Right now, as you sit watching this, you're orbiting a monster. Not just orbiting, but screaming through space at 500,000 miles per hour in a cosmic dance around something so massive, so dense, so utterly incomprehensible that it defies every human instinct about how reality should work. This monster sits 26,000 light-years away from us, lurking in the heart of our galaxy like a spider at the center of a web. It weighs 4.3 million times more than our Sun. It is invisible. It devours anything that ventures too close, and until very recently we had never actually seen it. This is Sagittarius A, pronounced Sagittarius A star, the supermassive black hole at the center of the Milky Way galaxy. For decades, astronomers knew something massive and dark inhabited the galactic core. They watched stars whip around an invisible point at speeds that should be impossible. They detected strange radio waves emanating from absolute darkness. They measured gravitational effects that could only be explained by a concentration of matter so dense that 4 million suns worth of mass had been compressed into a region smaller than Mercury's orbit around our Sun, but they couldn't see it. Black holes, by their very nature, are invisible. They don't emit light. They don't reflect light. They consume light, dragging it past a boundary called the event horizon, where the escape velocity exceeds the speed of light itself. But in May 2022, something extraordinary happened. The Event Horizon Telescope Collaboration, a worldwide network of radio observatories working in perfect synchronization, released the first actual image of Sagittarius A. Not an artist's conception, not a simulation, an actual photograph showing the glowing ring of superheated matter spiraling around the shadow of the black hole. The image showed a bright, asymmetrical ring with a dark center, exactly as Einstein's equations predicted a century ago. The shadow at the center isn't the black hole itself. It's the region where light can no longer escape, the point of no return. Around it, a disk of gas and dust heated to millions of degrees glows, with the fury of matter being torn apart by gravity so intense it warps the fabric of space-time. This achievement represents the culmination of decades of work. The story begins in February 1974, when astronomers Bruce Ballack and Robert Brown, using the Green Bank interferometer of the National Radio Astronomy Observatory, detected an unusual radio source in the direction of the constellation Sagittarius. They found something emitting synchrotron radiation, a particular type of electromagnetic energy created when charged particles spiral through magnetic fields at relativistic speeds. The source was incredibly compact and completely immobile, pinned in place by its own tremendous gravity. They named it Sagittarius A, marking it as the primary radio source at the galactic center. Later, the asterisk was added to distinguish the most intense point source from the broader radio emission region. That asterisk, that simple typographical mark, would become the symbol for one of the most important objects in astrophysics. But detecting radio waves is one thing. Proving you found a supermassive black hole is entirely different. For that, you need to watch how matter moves around it. You need to observe the gravitational effects. You need to catch stars in the act of orbiting the invisible monster. And that's exactly what two independent teams of astronomers began doing in the 1990s, spending decades tracking the fastest moving stars ever observed in human history. The realization that something truly extraordinary lived at our galaxy's heart came gradually, like a shape emerging from fog. Astronomers knew the galactic center was special. It glowed in radio waves. It showed unusual structure. But the breakthrough came with adaptive optics technology, which allowed telescopes to compensate for the blurring effects of Earth's atmosphere and see individual stars moving near the galactic core. What they saw was stunning. Stars racing around an invisible point at speeds that seemed impossible. Stars following perfect elliptical orbits around absolutely nothing visible. Stars moving so fast that general relativity's effects became measurable. These weren't ordinary stars drifting lazily through space. These were objects being whipped around by gravity so intense it bent their paths into tight loops, accelerating them to a significant fraction of light speed. The evidence was overwhelming and undeniable. Something with immense mass occupied a tiny volume at the exact center of the Milky Way. Something with a mass of 4.3 million suns crammed into a space no larger than the distance from the Sun to Neptune. Nothing else in known physics could explain this. No cluster of dead stars could be that compact without collapsing. No exotic matter configuration could resist gravitational collapse at that density. The only possible explanation was a supermassive black hole. In 2020, the Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea Ghez for proving this conclusively, for tracking the stellar orbits with such precision that all doubt evaporated. They had found the monster. Now the question became, what is it doing to our galaxy? And what secrets can it reveal about the nature of reality itself? If you're ready to journey into the heart of darkness, to understand what it means to live in a galaxy anchored by a cosmic monster, then hit that like button and subscribe. We're about to explore the most extreme physics laboratory in our cosmic neighborhood. Prepare yourselves. We begin. Before we dive into what Sagittarius A is and how it behaves, we need to understand the decades-long detective story that led to its discovery. This wasn't a simple matter of pointing a telescope at the sky and finding a black hole. It was a gradual accumulation of evidence, a slow revelation that took generations of astronomers working with increasingly sophisticated technology to piece together. The story of discovering Sagittarius A is inseparable from the story of learning to see through the veil of dust and gas that hides the galactic center from our view. The journey began long before 1974, when Balick and Brown made their discovery. In fact, it started with a fundamental question that astronomers grappled with for centuries. What is the structure of the Milky Way, and where do we sit within it? The answer to this question would eventually lead us to Sagittarius A, but the path was anything but straightforward. For thousands of years, humans looked up at the Milky Way and wondered what it was. The ancient Greeks thought it was milk spilled from the breast of the goddess Hera. Other cultures saw it as a river, a path, or a bridge to the heavens. It wasn't until Galileo pointed his telescope at the Milky Way in 1610 that humanity realized it was composed of countless individual stars. But even then, the structure of our galaxy remained mysterious. We were inside it, embedded in its disk, and couldn't step outside to see the overall shape. By the early 20th century, astronomers had figured out that the Milky Way was a disc-shaped collection of stars, but they argued fiercely about where we sat in that disk. Some thought the sun was near the center, others argued we were off to one side. The debate was settled in the 1920s by Harlow Shapley, who studied globular clusters, dense spherical collections of old stars that orbit the galactic center. By mapping the positions of these clusters, Shapley showed they formed a spherical halo around a point roughly 26,000 light-years away, in the direction of Sagittarius. The Sun and Earth were not at the center of the galaxy. We were out in the suburbs, orbiting around a distant center we couldn't directly see. This was a profound realization that continued the centuries-long process of removing Earth from any special place in the cosmos. Copernicus had shown we weren't at the center of the solar system. Later observations revealed the solar system wasn't at the center of anything special in the galaxy. Now, Shapley demonstrated that we were relegated to an ordinary location in the galactic disk, roughly 2/3 of the way out from the center. The true galactic center lay hidden behind vast clouds of dust and gas, invisible to the optical telescopes of the era. But what was at that center? Visible light observations couldn't answer the question because dust in the galactic plane absorbs optical light completely. The mechanism is straightforward but devastating for optical astronomy. Dust grains, tiny particles of carbon, silicates, and ice perhaps 1/1000th of a millimeter across, scatter and absorb visible light efficiently. A cloud of dust just a few light-years thick can block virtually all optical light passing through it. Between us and the galactic center lie thousands of light, years of dusty material, accumulated in the spiral arms and concentrated in the galactic plane. Looking toward the galactic center in visible wavelengths is like trying to see through a thick fog. You can make out vague shapes nearby, but anything more than a few thousand light-years away is completely obscured. This obscuration frustrated astronomers for decades. They knew the galactic center existed. They could infer its rough location from the distribution of stars and globular clusters, but they couldn't see what was actually there. Was it just more stars densely packed? Was there something unusual at the very center? Without direct observations, these questions couldn't be answered. The development of radio astronomy in the 1930s and 1940s would eventually provide the solution, but it took time for the technology to mature and for astronomers to realize what radio observations could reveal. Radio astronomy began almost accidentally in 1931 when Carl Jansky, an engineer working for Bell Telephone Laboratories, was investigating sources of static that interfered with radio communications. He built a large directional antenna designed to detect radio waves at a wavelength of about 14 meters. As he monitored the radio signals, Jansky noticed a steady hiss that rose and fell, with a period of about 24 hours. At first, he thought it might be related to the sun, but careful timing showed the period was actually 23 hours and 56 minutes, the sidereal day, the time it takes Earth to rotate once with respect to the distant stars rather than the sun. This meant the source was something in the distant universe, not in our solar system. By carefully mapping when the signal was strongest, Jansky determined it came from the direction of Sagittarius, toward the galactic center. He had detected radio waves from the Milky Way, the first observation of radio emission from beyond the solar system. At the time, this discovery generated some public interest, but little follow-up from the astronomical community. The technology was too new, the implications too uncertain. Radio astronomy remained a niche pursuit for years. The field exploded after World War II, when surplus radar equipment became available, and physicists trained in radio technology turned their attention to astronomy. In the late 1940s and early 1950s, astronomers began building dedicated radio telescopes and mapping the radio sky systematically. They discovered that the Milky Way glowed brightly in radio waves, with the strongest emission coming from the galactic center region, just as Jansky had found. But the early radio telescopes had poor angular resolution. They could tell that radio emission came from a general direction but couldn't pinpoint sources precisely. The entire galactic center appeared as a broad, diffuse radio glow. Improving angular resolution required larger telescopes or, more cleverly, interferometry. The principle of interferometry is elegant. Instead of building one enormous telescope dish, you build two or more smaller dishes separated by some distance and observe the same source with both. By carefully combining the signals, accounting for the slight difference in arrival time of radio waves at each dish, you can achieve the angular resolution of a telescope as large as the separation between dishes. The larger the separation, the finer the detail you can resolve. In the 1950s and 1960s, radio interferometry advanced rapidly. Astronomers built arrays of radio dishes separated by kilometers, then tens of kilometers, then eventually thousands of kilometers using very long baseline interferometry. These advances allowed them to resolve structure in the galactic center's radio emission. Instead of a uniform glow, they saw filaments, arcs, and compact sources. The region was far more complex than anyone had imagined. One of those compact sources would turn out to be Sagittarius A, but identifying it specifically required painstaking work. The galactic center is a radio-bright mess, filled with supernova remnants, regions of star formation, and various exotic objects all emitting radio waves. Distinguishing the central black hole from this background took sophisticated observations and careful analysis. The breakthrough came in 1974 when Balick and Brown used the Green Bank interferometer to achieve sufficient angular resolution to isolate individual compact sources. What made their discovery of Sagittarius A special was not just that they found a bright radio source, but that this source had unusual properties. It was incredibly compact, smaller than could be resolved even with the interferometer's fine resolution. It was also completely stationary. While other radio sources in the galactic center showed proper motion, moving slightly across the sky as they orbited the galaxy, Sagittarius A didn't move at all. It was pinned precisely at the dynamical center of the galaxy, the point around which everything else orbited. Moreover, the radio emission from Sagittarius A had a distinctive spectrum. Most radio sources in the galaxy emit synchrotron radiation, produced when electrons spiral through magnetic fields. Synchrotron radiation has a characteristic spectrum that depends on the energy distribution of the electrons and the strength of the magnetic field. Sagittarius A's spectrum was unusual, suggesting it was powered by processes different from typical supernova remnants or star-forming regions. These clues pointed towards something extraordinary at the galactic center, but proving it was a black hole required additional evidence. Radio observations alone couldn't do it. Astronomers needed to measure the mass of whatever was producing the radio emission, and the only way to do that was to watch how nearby objects moved under its gravitational influence. That meant observing stars orbiting close to Sagittarius A, which required infrared observations that could penetrate the dust and achieve high enough resolution to track individual stars. The development of infrared astronomy in the 1970s and 1980s opened new windows on the galactic center. Infrared light, with wavelengths longer than visible light but shorter than radio waves, can penetrate dust much better than optical light, while still allowing relatively high angular resolution. Early infrared surveys revealed that the galactic center was crowded with stars, far denser than anywhere in the solar neighborhood. But seeing individual stars moving required even better technology. The game changer was adaptive optics, developed in the 1990s. Earth's atmosphere is turbulent. Pockets of air at different temperatures and densities move around, causing the refractive index to fluctuate. This makes stars twinkle, which is charming to the naked eye, but disastrous for precision astronomy. It blurs images, limiting ground-based telescopes to angular resolutions far worse than their optics should theoretically achieve. Adaptive optics compensates for atmospheric turbulence in real time. The system uses a deformable mirror whose shape can be adjusted hundreds or thousands of times per second. A computer analyzes the distortion caused by the atmosphere, either by observing a bright star or by creating an artificial guide star with a laser, and commands the mirror to deform in exactly the right way to cancel the distortion. The result is that stars stop twinkling and appear as sharp points, allowing telescopes to achieve diffraction-limited resolution, comparable to what you'd get from a telescope in space. With adaptive optics installed on large infrared telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile, astronomers could finally see individual stars near Sagittarius A clearly enough to measure their positions and track their motion over time. Two independent teams, led by Reinhard Genzel and Andrea Ghez, began systematic programs to monitor these stars in the mid-1990s. They took images year after year, carefully measuring stellar positions to sub-millisecond precision, watching as the stars moved against the background. What emerged from these observations was stunning. The stars weren't drifting randomly. They were following precise elliptical orbits around the radio position of Sagittarius A. The orbits obeyed Kepler's laws perfectly. By applying those laws, the teams could calculate the mass of the central object. The answer came out to roughly 4 million solar masses, with increasing precision as more data accumulated, and the region containing that mass had to be tiny, no larger than the innermost stellar orbits, which passed within a few light hours of the center. This combination of enormous mass and tiny volume left only one possible explanation: a supermassive black hole. No other known object or configuration could pack millions of solar masses into a space smaller than the distance from the Sun to Neptune without collapsing into a black hole. The teams had found direct, incontrovertible evidence for a supermassive black hole at the center of the Milky Way. But science demands extraordinary evidence for extraordinary claims. The teams continued refining their measurements, tracking stars through complete orbits, measuring not just positions but also velocities through spectroscopy. Every new observation strengthened the case. By the early 2000s, the evidence was overwhelming. Multiple stars showed clear Keplerian orbits. The mass estimate converged on 4.3 million solar masses. The size constraint from the smallest observed stellar orbits eliminated all alternatives to a black hole. The coup de grace came in 2018 when the star S2 made its closest approach to Sagittarius A. This pericenter passage offered the perfect opportunity to test general relativity's predictions in a strong gravitational field. The teams observed S2 intensively during the months around pericenter, measuring its position and velocity with unprecedented precision. They detected the gravitational redshift predicted by Einstein, the stretching of light as it climbed out of the black hole's gravitational well. They later detected orbital precession, the slow rotation of S2's elliptical orbit caused by relativistic effects. Both observations matched general relativity's predictions perfectly and ruled out alternative theories of gravity. This body of work, spanning more than 2 decades of observations and involving hundreds of person-years of effort, earned Genzel and Ghez the 2020 Nobel Prize in Physics. The Nobel Committee's citation recognized them for the discovery of a supermassive compact object at the center of our galaxy, a carefully worded statement that acknowledged the object could only be a black hole given its observed properties. Together with Roger Penrose, who won the other half of the prize for theoretical work on black holes, They were honoured for transforming black holes from mathematical abstractions into observational realities. The road from Jansky's serendipitous discovery of radio waves from Sagittarius to the definitive proof of a supermassive black hole at the galactic centre spans 9 decades. It required the development of radio astronomy, infrared astronomy, interferometry, adaptive optics, and sophisticated data analysis techniques. It required hundreds of astronomers working across multiple generations, each building on the work of their predecessors. It required patience, as stars took years to complete orbits and reveal their secrets. And it required the conviction that even the most extreme predictions of physics, such as the existence of black holes from which light cannot escape, could be real features of the universe we inhabit. This historical arc reminds us that scientific progress is rarely linear or simple. Discovering Sagittarius A wasn't a eureka moment, but a gradual unveiling, a slow accumulation of evidence that built toward an inescapable conclusion. Each technological advance opened new possibilities. Each observation refined our understanding, and eventually the picture became clear. We live in a galaxy anchored by a supermassive black hole, a monster lurking in the darkness at the galactic heart. Astronomers needed a different kind of light, wavelengths that could penetrate the dust. The breakthrough came with radio astronomy. During World War II, researchers studying radar noticed that radio waves from space were interfering with their equipment. After the war, these researchers turned their attention to studying cosmic radio sources. Radio waves have much longer wavelengths than visible light, typically millimeters to meters rather than the tiny fractions of a micron of optical light. These long wavelengths allow radio waves to pass through dust clouds that block visible light, opening a window to the hidden universe. In the 1930s, Carl Jansky, an engineer working for Bell Telephone Laboratories, was investigating sources of static that interfered with radio communications. He built a rotating antenna system and discovered that some of the static came from beyond Earth. After careful analysis, he determined that the strongest radio emission came from the direction of the constellation Sagittarius, toward what we now know as the galactic centre. Jansky had made the first detection of radio waves from the centre of the Milky Way, though at the time, nobody understood what was producing them. Through the 1940s and 1950s, radio astronomy developed rapidly. Larger antennas, more sensitive receivers, and better techniques for mapping radio sources revealed that the galactic centre was incredibly bright in radio waves. There was clearly a lot happening there, though visible light observations showed nothing special. The contrast was striking. In optical light, the galactic centre region looked dark and unremarkable, hidden behind dust. In radio wavelengths, it blazed with energy. By the 1960s and 1970s, radio astronomers were mapping the galactic centre with increasing detail. They found extended structures, clouds of ionized gas, and compact sources of intense radio emission. The technology of the time couldn't resolve very fine details, but it was clear that the central parsec of the galaxy, the inner 3 light-years, contained something extraordinary. The radio emission patterns suggested violent processes, energetic events, magnetic fields, and matter in motion at high speeds. Then came the crucial advance: very long baseline interferometry, or VLBI. This technique combines signals from multiple radio telescopes separated by large distances, effectively creating a virtual telescope as large as the separation between them. The farther apart the telescopes, the finer the details you can resolve. VLBI observations of the galactic centre in the 1970s revealed that much of the radio emission came from a single, incredibly compact source. This source was so small that even with continent-spanning arrays of telescopes, it appeared as essentially a point. That's when Ballack and Brown made their discovery. On February 13th and 15th, 1974, using the Green Bank interferometer, they identified and characterized Sagittarius A. They found that this radio source was uniquely compact, uniquely bright, and completely stationary. Most radio sources in the sky move slightly over time due to the motion of the galaxy and the Sun's orbit around the galactic centre. But Sagittarius A didn't move. It sat at the exact rotational centre of the Milky Way, the point around which everything else orbited. This wasn't a random radio source that happened to be in that direction. This was something at the dynamical centre of our galaxy. But what was it? The radio properties alone couldn't answer that. The source was too small to be a star cluster. It was too bright to be a single star. The emission was non-thermal, meaning it didn't come from hot gas radiating like a black body, but from synchrotron radiation, high-energy particles spiraling through magnetic fields. This suggested some kind of compact energetic object, but the exact nature remained unclear. Throughout the 1980s, astronomers debated whether a massive black hole resided at the galactic centre. The idea was controversial. Black holes had been predicted by general relativity, and stellar mass black holes were thought to exist as the endpoints of massive star evolution. But supermassive black holes containing millions of solar masses seemed exotic. Some astronomers argued that the central mass could be a dense cluster of dark objects, perhaps neutron stars or stellar mass black holes, rather than a single supermassive black hole. The debate intensified as new observations came in. Infrared observations, which could penetrate the dust better than visible light though not as well as radio, revealed stars moving at high velocities near the galactic centre. Radio observations showed wisps and structures of gas swirling around Sagittarius A X-ray observations detected hot plasma and variable emission. Each new piece of evidence suggested something massive and compact, but nothing was definitive. The real breakthrough came with adaptive optics in the 1990s. Earth's atmosphere is constantly in motion, causing starlight to twinkle and blur. This atmospheric turbulence limits how sharp an image a ground-based telescope can obtain. Adaptive optic systems use deformable mirrors that change shape hundreds or thousands of times per second to compensate for atmospheric distortions, sharpening images dramatically. Applied to large infrared telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile, adaptive optics allowed astronomers to track individual stars within a light year of Sagittarius A. The stars they found were moving incredibly fast. One star in particular, later designated S2, caught everyone's attention. Between the year 1995 and 2002, astronomers watched S2 trace out a significant portion of an elliptical orbit around Sagittarius A. By plotting the star's position year after year, they could determine the orbit's size, shape, and period. The results were stunning. S2's orbital period was only about 16 years, incredibly short for something orbiting the galactic centre. Its orbit brought it within 17 light-hours of Sagittarius A, and at closest approach, it reached speeds exceeding 7,000 km per second. Using Kepler's laws, which relate orbital period and distance to the central mass, the teams calculated that Sagittarius A contained about 4 million solar masses. And because S2 passed so close without colliding with anything, that mass had to be concentrated in a volume no larger than a few light-hours across. There was only one explanation: a supermassive black hole. This conclusion was reinforced by tracking additional stars with shorter orbits, by improving measurements of S2's orbit, and by watching stars over multiple complete orbits. By the early 2000s, the evidence was overwhelming. Sagittarius A was indeed a black hole, and a massive one at that. The discovery earned Reinhard Genzel and Andrea Ghez the Nobel Prize in 2020, recognizing their decades of work transforming an invisible monster into one of the best-studied objects in astrophysics. But even with that confirmation, mysteries remained. How did the black hole form? What was it doing to the surrounding environment? Why was it so dim compared to its mass? How did matter flow into it? What would it look like up close? These questions drove the next generation of observations, culminating in the Event Horizon Telescope's historic images and the ongoing multi-wavelength campaigns that continue to reveal new aspects of the monster at our galaxy's heart. To understand Sagittarius A, you first need to understand what a black hole actually is, and that requires throwing away most of your intuitions about how matter and space work. We live in a universe where matter exists in space, where space is a container, a backdrop, an empty stage on which the drama of existence plays out. But Einstein's general theory of relativity revealed something profoundly different. Space isn't a container. Space is a thing, a fabric that can be bent and stretched and warped by the presence of mass and energy. Massive objects don't just sit in space, they reshape it, creating curves and dimples in the geometry itself. We experience this reshaping as gravity. Imagine space-time as a stretched rubber sheet. Place a marble on it and the sheet dips slightly. Place a bowling ball on it and the dip becomes pronounced, and nearby marbles will roll toward the depression. Replace the bowling ball with something infinitely dense and infinitely heavy, and the dip becomes a funnel, a pit, a bottomless well from which nothing can escape. That's a black hole. It's a region where space-time has been curved so severely that it forms a one-way surface. Cross that surface, called the event horizon, and you cannot return. Not because some force holds you in, but because all paths through space-time, all possible futures, lead inward. The geometry of reality itself has been folded into a trap. Black holes come in different sizes. Stellar mass black holes form when massive stars, perhaps 10 to 100 times the mass of the Sun, exhaust their nuclear fuel and collapse. The star's core implodes in a fraction of a second, compressing matter to densities beyond comprehension. If enough mass remains after the supernova explosion that accompanies this death, gravity crushes the core past the point where even atomic structure can resist. Electrons and protons merge into neutrons, and then even neutron degeneracy pressure fails. The matter collapses through every possible state until it forms a singularity, a point of infinite density hidden behind an event horizon perhaps 10 to 100 kilometers across. These stellar black holes litter the galaxy by the millions, invisible remnants of dead stars. But supermassive black holes are different beasts entirely. They contain millions or billions of solar masses. Sagittarius A at 4.3 million solar masses is relatively modest by supermassive black hole standards. The black hole at the centre of the galaxy Messier 87, which the Event Horizon Telescope imaged in 2019, weighs 6.5 billion solar masses, more than 1,000 times heavier than our galactic monster. The black hole in the galaxy Holmberg 15Ia may contain 40 billion solar masses, nearly 10,000 times more massive than Sagittarius A. These are objects so immense that despite their incredible density, their event horizons stretch across dimensions comparable to our solar system. The event horizon of Sagittarius A has a radius of about 12 million kilometers, roughly 0.08 astronomical units. That's about 17 times larger than the Sun. Everything within that boundary is lost. Light emitted from just inside the horizon can never reach an outside observer. Time itself, as measured by a distant observer, appears to stop at the horizon. An object falling toward the event horizon would appear to slow down, its clock ticking more and more slowly as it approached, frozen in time at the threshold, though from the object's perspective it would cross the horizon in finite time and quickly reach the central singularity. But here's what makes Sagittarius A so important for astrophysics. It's close. At 26,000 light-years away, it's the nearest supermassive black hole to Earth. This proximity, combined with its relatively modest size, makes it ideal for detailed study. The black hole in M87 is vastly more massive, but it sits 53 million light-years away. Despite being over 1,000 times heavier, M87's black hole and Sagittarius A appear roughly the same size in the sky due to the distance difference. This happy coincidence means we can observe Sagittarius A with the same angular resolution as M87, allowing direct comparison between supermassive black holes of different masses and different environments. The position of Sagittarius A in the sky lies near the border between the constellations Sagittarius and Scorpius, about 5.6 degrees south of the ecliptic, near the butterfly cluster. But you can't simply point a telescope at it and look. The galactic center is one of the most crowded, dusty, chaotic regions imaginable. Stars pack together thousands of times more densely than in our solar neighborhood. Clouds of gas and dust absorb visible light, making the region completely opaque in optical wavelengths. Only 1 in 10 billion photons of visible light emitted near Sagittarius A reaches Earth, the rest absorbed by the intervening material. This is why the black hole remained hidden for so long despite being the brightest radio source in our sky from the galactic center region. To see through this cosmic fog, astronomers must use wavelengths that can penetrate dust. Radio waves pass through gas and dust relatively easily, which is why Sagittarius A was first detected as a radio source. Infrared light also penetrates better than visible light, allowing infrared telescopes to see individual stars near the galactic core. X-rays from the superhot gas surrounding the black hole also make it through, painting a different picture of the environment. Each wavelength reveals different aspects of the monster and its domain. The radio emission comes from electrons spiraling through magnetic fields in the accretion flow. The infrared emission shows starlight and warm dust. The X-rays betray gas heated to tens of millions of degrees by friction and compression as it spirals toward oblivion. Understanding the size and mass of Sagittarius A required piecing together observations across decades. The mass determination came from watching stars orbit around it and using Kepler's laws of orbital motion. If you know how far a star is from the center and how fast it orbits, you can calculate the mass of whatever it's orbiting. The more precise your measurements of stellar positions and velocities, the better your mass estimate. Teams led by Reinhard Genzel in Germany and Andrea Ghez in the United States spent years refining these measurements, tracking stars year after year as they looped around the invisible center. Their results agreed: 4.3 million solar masses, give or take a tiny fraction of a percent. The precision is staggering. We know the mass of the black hole at the center of our galaxy better than we know the masses of many nearby stars. The size constraint came from realizing that the orbiting stars pass extremely close to the black hole without colliding with anything. Some stars approach within 120 astronomical units of the black hole's center, about 4 times Neptune's distance from the Sun. If Sagittarius A were a cluster of stars or some extended object, these orbiting stars would pass through it and show signs of disruption. They don't. The object is compact, smaller than the closest stellar approaches. Combined with a mass measurement, this proves the object is a black hole. Nothing else can pack that much mass into that smaller volume without collapsing into a black hole. This makes Sagittarius A an extreme environment by any measure. The gravitational acceleration near the event horizon exceeds anything we can create in laboratories by factors of billions. Tidal forces near the event horizon are strong enough to stretch and compress objects until they disintegrate. Magnetic fields in the accretion flow rival the strongest fields in the universe. Particles accelerate to within a tiny fraction of light speed. Space-time curvature becomes so severe that light from behind the black hole bends around it, creating multiple images and strange visual effects. This is nature's ultimate physics laboratory, a place where the laws of the universe are pushed to their breaking points, and somehow, incredibly, Einstein's century-old equations still describe what happens with uncanny accuracy. The most dramatic evidence for Sagittarius A's existence comes from watching stars move. Not just any stars, but a particular group designated the S stars, named for their proximity to Sagittarius A itself. These stars orbit so close to the black hole and move so fast that they provide a natural laboratory for testing gravity under the most extreme conditions accessible to observation. Among all the S stars, one stands out as particularly important: S2, also known as S02 in some catalogues. This star has become one of the most intensely studied objects in astronomy. S2 is a blue supergiant star, roughly 14 times more massive than the Sun when it formed. Though it may have lost some mass over time, it's spectacularly bright in infrared wavelengths, making it visible despite the dust and gas between us and the galactic center. More importantly, it follows an extraordinarily tight orbit around Sagittarius A. The orbital period is 16.05 years. The orbit is highly elongated, an eccentric ellipse that brings S2 screaming past the black hole at its closest approach, called pericenter, and then sends it swinging out to more than 1,000 astronomical units at epicenter, its farthest point. At pericenter, S2 passes within 120 astronomical units of Sagittarius A, roughly the distance from our Sun to Pluto. That might sound far, but remember that Sagittarius A's event horizon is only 0.08 astronomical units across. S2 passes within 1,400 Schwarzschild radii of the black hole, where 1 Schwarzschild radius is the radius of the event horizon. This is close enough that relativistic effects become significant and measurable. The speeds involved are staggering. At pericenter, S2 reaches velocities of 7,150 km per second, about 17 million miles per hour. That's 2.7% of the speed of light. Nothing in the solar system moves that fast. Mercury, the fastest planet, orbits at 48 km per second. Earth moves at 30 km per second. S2 is travelling 160 times faster than Earth orbits the Sun. At those speeds, time dilation becomes noticeable. A clock on S2 would tick slightly slower than a clock far from the black hole, by about a few parts in 10,000. That might sound tiny, but it's measurable with modern instruments, and it provides a direct test of general relativity in a strong gravitational field. Astronomers have watched S2 complete multiple full orbits since the late 1990s. Every observation refines the orbital parameters and tests whether the orbit matches predictions from general relativity or deviates in ways that would suggest new physics. The orbit is so well characterized that astronomers can predict S2's position months in advance and schedule observations for maximum scientific return. The last pericenter passage occurred in May 2018, and astronomers around the world trained their most powerful telescopes on the event, watching to see if S2 would behave exactly as Einstein predicted or reveal something unexpected. What they saw was a triumph for general relativity. As S2 approached the black hole, its light shifted toward longer, redder wavelengths. This is gravitational redshift, a prediction of general relativity that says light climbing out of a gravitational well loses energy and shifts to longer wavelengths. S2 showed both velocity redshift, from its motion away from us, and gravitational redshift from the black hole's gravity. By carefully separating these effects, astronomers detected the gravitational redshift at 5 sigma significance, meaning less than 1 chance in a million that it was a statistical fluke. The measured redshift agreed with general relativity within the 10% measurement precision. S2 also showed something called Schwarzschild precession. In Newtonian gravity, if a star orbits in an ellipse, the ellipse remains fixed in space, with the pericenter and apocenter always at the same locations. But in general relativity, the ellipse slowly rotates. The point of closest approach shifts slightly with each orbit, causing the ellipse to precess like a wobbling top. The amount of precession depends on how strong the gravitational field is and how close the orbit comes to the black hole. For S2, the precession is about 12 arc-minutes per orbit, 1/5 of a degree. That might sound tiny, but it's detectable with modern astrometry, the precise measurement of stellar positions. By 2020, the precession had been detected at 7 sigma significance, another ringing confirmation of general relativity. These observations earned Reinhard Genzel and Andrea Ghez a share of the 2020 Nobel Prize in Physics. The citation read, "For the discovery of a supermassive compact, object at the center of our galaxy, the prize recognized decades of painstaking work tracking stars in the galactic center, developing new instruments and techniques, and ultimately proving beyond doubt that Sagittarius A is a supermassive black hole. It's one thing to theorize that such objects exist. It's entirely another to actually find one and measure its properties with exquisite precision. But S2 isn't alone. Dozens of other stars orbit Sagittarius A at various distances, each providing additional data points for testing gravity and mapping the black hole's environment. Some stars have longer, wider orbits than S2, others have shorter, tighter orbits that bring them even closer to the black hole. In 2020, astronomers reported the discovery of S474, a star with an orbital period of only 12 years and a pericenter distance of just 12.6 astronomical units, almost as close as Saturn is to our Sun. At pericenter, S4714 reaches 8% of light speed, about 24,000 kilometers per second. This is the current record holder for the closest confirmed stellar approach to Sagittarius A. Another notable star is S0102, also called S55, which has an orbital period of 11.5 years, slightly shorter than S4714, but with a somewhat larger pericenter distance of about 260 astronomical units. These short-period stars are incredibly valuable for testing relativity because they complete orbits quickly by astronomical standards, allowing researchers to observe multiple orbits within a single career. The more orbits observed, the better the orbital parameters can be determined and the more sensitive tests of general relativity become. The S-stars form a stellar cluster surrounding the black hole. Within the central parsec, roughly 3 light-years, hundreds of stars orbit Sagittarius A. Many are young, massive stars that shouldn't exist there because the tidal forces near a supermassive black hole should prevent star formation. The leading theory is that these stars formed farther out and then migrated inward through dynamical friction and gravitational interactions with other stars. They represent the survivors of a brutal cosmic environment where stellar collisions and close encounters are common. These stars don't just test gravity, they also probe the environment around the black hole. As they orbit, they plow through whatever gas and dust surrounds Sagittarius A, experiencing drag that slightly slows them down. By measuring tiny changes in orbital velocities, astronomers can estimate the density of material in the accretion flow at various distances from the event horizon. This technique has revealed that the gas density at around 1,000 Schwarzschild radii is higher than previously thought, providing crucial data for understanding how black holes are fed. The observation of stellar orbits represents one of the great achievements of modern astronomy. To track these stars, astronomers use adaptive, optic systems that deform telescope mirrors hundreds or thousands of times per second to compensate for atmospheric turbulence. They employ infrared cameras sensitive enough to detect faint stars through the galactic centers obscuring dust. They process years of data to extract tiny positional shifts and velocity measurements. The result is a moving portrait of a gravitational monster, revealed through the motion of its captive stars, each one a test particle probing the structure of warped spacetime. While Sagittarius A holds a special place as our nearest supermassive black hole, it's far from alone in the universe. Every large galaxy appears to host a supermassive black hole at its center, and studying how these monsters compare reveals fundamental insights into how galaxies and black holes co-evolve. The diversity is staggering, ranging from millions to tens of billions of solar masses, from quietly sleeping to violently active. M87, the first black hole imaged by the Event Horizon Telescope in 2019, resides in the giant elliptical galaxy Messier 87, 53 million light-years away. M87 weighs 6.5 billion solar masses, over 1,500 times more massive than Sagittarius A. Despite the enormous mass difference, the images look remarkably similar. Both show a bright ring surrounding a dark shadow with asymmetric brightness. This similarity is profound because it suggests the physics of black holes is universal. The geometry of warped space-time, the accretion flow structure, and the role of magnetic fields follow similar patterns regardless of mass. But there are important differences. M87 is actively feeding at a much higher rate, powering a spectacular jet that shoots out at near-light speed and extends thousands of light-years. The jet contains as much energy as converting the entire Sun's mass to pure energy every few years. Sagittarius A shows no large-scale jet, reflecting different environments and feeding states. M87 sits in a dense galaxy cluster, with abundant hot gas to feed the black hole. The Milky Way's less dense environment starves Sagittarius A by comparison. Quasars represent supermassive black holes in their most active state, consuming matter so rapidly they outshine entire galaxies. Some quasars emit the energy equivalent of 1 trillion suns, visible across billions of light-years. One quasar, J313 1806, hosts a 1.6 billion solar mass black hole, despite existing when the universe was only 670 million years old. This poses serious challenges to formation theories because there hasn't been enough time for normal growth. The relationship between black hole mass and galaxy properties reveals deep connections. The black hole mass typically equals about 0.1% of the bulge mass. This M-sigma relation suggests black holes and galaxies co-evolve through feedback processes. When black holes actively accrete, they inject energy into surrounding gas, regulating star formation and creating balance between black hole and galaxy growth. Sagittarius A fits this pattern. The Milky Way's bulge contains about 20 billion solar masses, and Sagittarius A's 4.3 million solar masses corresponds to roughly 0.02%, slightly lower than typical but within observed ranges. The diversity and activity is equally striking. Active galactic nuclei range from powerful quasars and blazars to moderately active Seyfert galaxies to low luminosity AGN like Sagittarius A. Many galaxies show evidence of past activity that has ceased, with expanding shells of gas and cavities from ancient jets. Black holes cycle through active and quiescent phases depending on fuel availability. The comparison teaches us that Sagittarius A is both typical and special. It's typical in mass for a galaxy like the Milky Way, typical in its quiescent state, typical in matching the M-sigma relation. But it's special in being close enough to study in extraordinary detail, serving as our Rosetta Stone for understanding all supermassive black holes everywhere. On May 12, 2022, astronomers held simultaneous press conferences around the world to announce something extraordinary. The Event Horizon Telescope collaboration had successfully imaged Sagittarius A, capturing the first direct visual evidence of the black hole at our galaxy's center. The image showed a glowing, donut-shaped ring of emission surrounding a dark shadow, exactly as general relativity predicted. The shadow represents the region from which light cannot escape, the photon sphere just outside the event horizon. The bright ring is superheated gas in the accretion disk, matter spiraling toward its doom at speeds approaching light speed, heated by friction and magnetic compression to millions of degrees. This achievement required technology and coordination on a scale rarely attempted in astronomy. The Event Horizon Telescope isn't a single telescope. It's a global network of radio observatories scattered across the planet, all synchronized to observe the same target at the same time. The technique is called Very Long Baseline Interferometry, or VLBI. Instead of building one enormous telescope dish, which would be impossibly expensive and physically challenging, VLBI uses multiple smaller telescopes separated by thousands of kilometers. By carefully synchronizing their observations using atomic clocks locked to GPS time standards, astronomers can combine the data as if all the telescopes were part of one gigantic dish, with a diameter equal to the distance between them. For imaging Sagittarius A, the Event Horizon Telescope used 8 radio observatories on 6 geographical sites. The array included telescopes in Hawaii, Arizona, Mexico, Chile, Spain, and Antarctica. From the South Pole Telescope in Antarctica to the James Clerk Maxwell Telescope in Hawaii, the network spanned nearly the entire diameter of Earth, creating a virtual telescope roughly 13,000 kilometers across. This gives the array an angular resolution of about 25 microarc seconds, fine enough to read newspaper text in New York from Paris, or to resolve the event horizon shadow of Sagittarius A despite it being 26,000 light-years away. The observations took place over several days in April 2017. Each telescope pointed toward the galactic center and recorded radio waves at a wavelength of 1.3 millimeters, corresponding to a frequency of 230 gigahertz. At these wavelengths, Earth's atmosphere is partially transparent, though water vapor still causes significant absorption. The telescopes had to be located at high-altitude, dry sites to minimize atmospheric interference. During the observations, each telescope recorded approximately 350 terabytes of data per day. The total data volume exceeded 5 petabytes, more information than the entire internet could transmit in 2017. This enormous dataset had to be physically transported by airplane to central processing facilities, because even modern internet connections couldn't handle the bandwidth requirements. The physical process of getting the data to the correlation centers became a logistical challenge in itself. The South Pole Telescope, one of the 8 observatories in the array, presented particular difficulties. Antarctica is accessible only during the austral summer, roughly October through February. The observations happened in April 2017, during the Antarctic winter when the station is completely cut off from the outside world. The hard drives containing the telescope's data had to wait at the South Pole until the first flights could land in December 2017, 8 months after the observations. Only then could the data be shipped to the correlation centers in Massachusetts and Germany, where it would be combined with data from the other telescopes. Each observatory used atomic clocks, incredibly precise timekeeping devices that lose less than a second over millions of years, synchronized to GPS satellites. These clocks time-stamped every measurement with nanosecond precision. This synchronization was critical because the technique relies on comparing the arrival times of radio waves at different telescopes. Light travels at 300,000 kilometers per second, but at radio wavelengths, we're looking at specific peaks and troughs of electromagnetic waves. If 2 telescopes separated by several thousand kilometers observe the same wavefront, the time difference in arrival tells you about the source's position in the sky with extreme precision. The correlation process itself was computationally intensive beyond belief. Supercomputers at MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy worked for months processing the data. They had to align the signals from all 8 telescopes, account for Earth's rotation during observations, correct for atmospheric delays, and combine everything into measurements of visibility, essentially Fourier transform components that describe the source's brightness distribution on the sky. But here's where imaging Sagittarius A became uniquely difficult compared to M87. The gas orbiting Sagittarius A completes a circuit in mere minutes. During a single night's observation, the source changes dramatically. Imagine trying to photograph a hummingbird in flight using a camera that can only take pictures at a rate of 1 frame per several seconds from different angles, and you only get data from 8 different positions around the bird, not a complete view. The hummingbird's wings are constantly moving, changing position between each snapshot. When you try to reconstruct what the bird looks like, you end up with a blurred mess because the different snapshots don't align. The Event Horizon Telescope team faced this exact problem. They couldn't simply combine all the observations into one image because the source itself was changing faster than they could image it. The solution required developing entirely new image reconstruction algorithms. The team created what they called snapshot imaging methods that could account for the source variability. They effectively reconstructed thousands of different possible images, each representing the source at different moments, then averaged them together in clever ways to find the consistent features. These algorithms incorporated physical models of how accretion disks behave. The team didn't just blindly fit the data, they used simulations of black hole accretion based on general relativistic magnetohydrodynamics to guide the reconstruction. These simulations predicted what a 4 million solar mass black hole surrounded by hot gas should look like from different viewing angles, with different spins, different accretion rates, and different magnetic field configurations. The algorithms searched for images that matched both the telescope data and the physical models. Another challenge came from scattering. The radio waves from Sagittarius A pass through the interstellar medium, the thin gas and plasma between stars. This medium isn't perfectly transparent. It contains free electrons that scatter radio waves, blurring the image like looking through frosted glass. The scattering is stronger at longer wavelengths and diminishes at shorter wavelengths. This is why the Event Horizon Telescope operates at 1.3 mm wavelength instead of longer wavelengths. Even so, scattering isn't negligible. The team had to model the scattering based on observations at multiple wavelengths. They essentially had to figure out how the frosted glass distorts the image, then computationally remove that distortion. This required careful analysis and added uncertainty to the final image. Different scattering models produced slightly different images, and the team had to ensure their results were robust against these uncertainties. Processing the data took years. The observations happened in April 2017. The M87 image was released in April 2019, 2 years later. The Sagittarius image didn't come out until May 2022, 5 years after the observations. This delay wasn't because the team was slow, it was because imaging Sagittarius A was so much harder than imaging M87. The variability, the scattering, the faintness of the source all combined to make the data analysis extraordinarily difficult. When the image finally emerged, it validated decades of theoretical work. The bright ring was about 50 microarc seconds across, matching predictions for a black hole of this mass. The shadow in the center was the right size. The asymmetry and brightness around the ring matched expectations for a rotating disk of gas viewed at an inclination. General relativity predicted all these features, and the observations confirmed them. But the image also raised new questions. Why is the brightness distribution around the ring so variable? Different reconstruction methods and different subsets of the data showed the bright spot in different locations. This isn't an artifact of the imaging process, it's real variability in the source. The gas distribution around Sagittarius A is turbulent and constantly changing. Future observations with better time resolution and more telescopes might capture this variability directly, essentially making movies of gas swirling around the black hole. The Event Horizon Telescope collaboration also had to grapple with systematic uncertainties. How do you know your image is correct when you're imaging something no one has ever seen before? The team used multiple independent imaging pipelines developed by different groups using different algorithms. If all the pipelines produced similar images, that gave confidence the results were real and not artifacts of any particular method. They also tested their algorithms on simulated data, where they knew the true answer, verifying that the methods could recover the correct image from synthetic observations. The final image released to the public was actually an average of many images produced by different algorithms. This average represented the consensus view, the features that appeared consistently across different approaches. The team also produced images showing the range of variation, demonstrating what aspects of the image were certain and what aspects were uncertain. This transparency about uncertainty is crucial in science. It's not enough to show a pretty picture. You have to show how confident you are in each feature of that picture. Processing the data took years. The challenge wasn't just the volume of information, but the nature of the target itself. Sagittarius A is much smaller than M87, the black hole the Event Horizon Telescope imaged in 2019. Being smaller and closer to us, it obtends a similar angle on the sky as M87, making it theoretically just as imageable. But there's a critical difference in behaviour. The black hole in M87 is massive and relatively slow changing. The hot gas in its accretion disk takes days to orbit. During the hours of observation, M87 remained essentially static, making image reconstruction straightforward. Sagittarius A is different. The gas orbiting it completes a full circuit in just minutes to hours. During a single night's observation, the source changes dramatically. Imagine trying to photograph someone's face while they're rapidly moving their head, and you only get to take pictures from 8 different angles at different times. You end up with a blurred, confusing mess. The Event Horizon Telescope team had to develop new algorithms to account for this rapid variability, essentially reconstructing thousands of possible images and averaging them together to find the features that appeared consistently. Another complication came from interstellar scattering. The radio waves from Sagittarius A pass through clouds of ionized gas between us and the galactic center. These clouds act like an imperfect lens, blurring and scattering the radio waves. The effect is strongest at longer wavelengths, which is why the Event Horizon Telescope operates at very short radio wavelengths, where scattering is minimized but not eliminated. Even so, the team had to carefully model and remove scattering effects from their data. The final image that emerged from this computational marathon showed a bright asymmetric ring about 51.8 microarc seconds across, surrounding a dark shadow. The ring isn't uniform in brightness. It shows bright spots and dimmer regions, reflecting the turbulent, clumpy nature of the accretion flow. These brightness variations change on timescales of minutes, which is why the final image represents an average over many possible configurations. Some images from the reconstruction showed the bright spot on the eastern side of the ring. Others showed it on the western side or southern side. By averaging them together, the collaboration produced an image showing the most consistent features while suppressing transient variations. The shadow at the center is slightly smaller than the bright ring, about 41.5 microarc seconds in diameter. This matches theoretical predictions for a black hole of Sagittarius A's mass remarkably well. The shadow isn't the event horizon itself, but rather the photon sphere, a region where light can orbit the black hole before either escaping to infinity or falling in. General relativity predicts the shadow should be roughly 2.6 times larger than the Schwarzschild radius of the event horizon. For Sagittarius A, that works out to about 42 microarc seconds, in excellent agreement with the observation. The success with Sagittarius A came 3 years after the Event Horizon Telescope's first triumph, imaging the supermassive black hole in the galaxy M87. That image, released in April 2019, was the first ever direct photograph of a black hole. It showed a similar bright ring and dark shadow structure, but for a black hole 6.5 billion solar masses, over 1,500 times more massive than Sagittarius A. Having images of both black holes allows astronomers to compare how black holes of vastly different masses behave. Remarkably, despite the enormous mass difference and the different galaxy types, the images look strikingly similar. Both show the predicted ring and shadow structure. Both have asymmetric brightness distributions. Both confirm that general relativity works even in these extreme environments. The Event Horizon Telescope collaboration didn't stop with a single image. In March 2024, they released a new image of Sagittarius A showing the polarization of the radio emission. Polarization refers to the orientation of the electromagnetic wave's oscillation. Light becomes polarized when it interacts with magnetic fields, and the polarization pattern reveals the structure of those fields. The polarized image of Sagittarius A shows strong, organized magnetic fields spiraling around the black hole, similar to those seen around M87. These magnetic fields play a crucial role in channeling gas into the accretion flow and potentially in launching jets of matter from near the event horizon. Future observations promise even more detail. The Event Horizon Telescope is adding new telescopes to its network, increasing both sensitivity and angular resolution. With more telescopes observing at the same time, the collaboration can fill in gaps in the coverage and produce higher quality images. There's also discussion of extending observations to shorter wavelengths, which would provide sharper views of the black hole, but require overcoming technical challenges with atmospheric water vapor absorption. The ultimate goal is to make movies showing how the gas flows around the black hole in real time, revealing the dynamics of matter spiraling toward oblivion. The event horizon. Telescope's achievement with Sagittarius A represents decades of work by hundreds of scientists across dozens of institutions. It required developing new telescope technology, inventing sophisticated data analysis algorithms, and coordinating observations across the globe with split-second timing. The result is an image that confirms one of the most profound predictions of Einstein's theory, that concentrations of mass can curve space-time so severely that they create one-way boundaries, black holes from which nothing can escape. We've seen the shadow of the monster. Now comes the work of understanding what it's doing to our galaxy. Capturing an image of Sagittarius A required the Event Horizon Telescope's global network of radio observatories, but understanding the black hole's full story demands observations across the entire electromagnetic spectrum. From radio waves to gamma rays, each wavelength reveals different aspects of the monster and its environment. The arsenal of telescopes and instruments trained on Sagittarius A represents humanity's most sophisticated technology for observing the cosmos. Radio astronomy is where the story began. Radio. Telescopes use large metal dishes to collect radio waves, electromagnetic radiation with wavelengths ranging from millimeters to meters. The advantage is that radio waves penetrate dust and gas that completely blocks visible light, making radio the only way to see through the galactic center's obscuring material. The Very Large Array in New Mexico, a collection of 27 radio dishes each 25 meters across, has been instrumental in mapping the radio emission from Sagittarius A and the surrounding region. The Atacama Large Millimeter Array, ALMA, in Chile consists of 66 precision antennas working together at wavelengths perfect for studying cold molecular gas and hot accretion flow emission. Infrared astronomy is essential for studying individual stars near the black hole. The Keck Observatory in Hawaii has been tracking S-stars for over 2 decades using advanced adaptive optics. The gravity instrument on the Very Large Telescope combines light from 4 8-meter telescopes to achieve extraordinary precision, measuring stellar positions to 10 microarc seconds. This precision allowed gravity to detect hotspots in the accretion flow, orbiting at 30% of light speed, directly observing matter just outside the event horizon. X-ray astronomy reveals gas heated to millions of degrees. NASA's Chandra X-ray Observatory has monitored Sagittarius A since 1999, tracking flares and characterizing the black hole's variability. The New Star Telescope extends observations to higher energies, revealing the most energetic processes. The European Space Agency's XMM Newton excels at spectroscopy, mapping the distribution of hot iron and other elements in gas clouds near the black hole. At even higher energies, gamma-ray astronomy takes over. The Fermi Gamma Ray Space Telescope discovered mysterious gamma-ray bubbles extending 50,000 light-years above and below the galactic center, possibly remnants of past activity from Sagittarius A. Ground-based observatories like HESS map ultra-high energy gamma rays near the galactic center. The James Webb Space Telescope, launched in 2022, has observed flickering and flaring from Sagittarius A with unprecedented infrared sensitivity, revealing rapid variations on minute timescales. These observations show the innermost accretion flow is highly dynamic. Each observatory contributes a piece of the puzzle. By combining observations across wavelengths, astronomers construct a multispectral portrait that no single instrument could provide. Coordinated campaigns where multiple telescopes observe simultaneously are particularly valuable, especially when unusual events like major flares occur. The suite of observatories studying Sagittarius A represents billions of dollars of investment and decades of technological development. Together, they've transformed a radio source discovered in 1974 into one of the most intensively studied objects in astronomy. For most of its existence, Sagittarius A has been remarkably quiet. It sits at the center of our galaxy like a sleeping giant, barely sipping the gas and dust around it. Observations across the electromagnetic spectrum show that the black hole is extremely underluminous for its mass. It emits only a tiny fraction of the energy that its gravity could extract from infalling matter. If Sagittarius A were actively feeding, if it were consuming gas at anything close to the maximum rate gravity allows, it would shine with the power of a quasar, outshining every star in the galaxy combined and making the Milky Way's core visible across billions of light years. Instead, it's one of the faintest supermassive black holes known, emitting less energy than a typical star. This quiescence isn't permanent though. Occasionally the monster stirs. Astronomers monitoring Sagittarius A across wavelengths have detected flares, sudden brightenings that last for hours before fading back to the baseline quiet state. These flares appear in X-rays and infrared light, indicating that something in the immediate vicinity of the black hole, within just a few Schwarzschild radii of the event horizon, is suddenly heating up and radiating intensely before cooling down or disappearing across the horizon. The flares are not subtle. In typical quiet mode, Sagittarius A emits X-rays at a low, steady level. But during a flare, the X-ray luminosity can increase by factors of 10, 100, or even more. The most dramatic flare ever observed occurred on September 14, 2013, when NASA's Chandra X-ray Observatory detected an outburst 400 times brighter than Sagittarius A's normal X-ray emission. This megaflare lasted for several hours before subsiding. Astronomers watched in real time as the black hole's immediate environment lit up with radiation, then faded back to darkness. Another spectacular event happened on October 20, 2014, when Chandra observed another enormous flare, this one 200 times brighter than the usual output. Then in May 2019, astronomers using the Keck Observatory witnessed Sagittarius A become 75 times brighter than normal in infrared light. These aren't rare one-off events. Smaller flares happen roughly daily, with the black hole brightening by factors of 3 to 10 before returning to baseline. The larger megaflares occur less frequently, perhaps a few times per year, but when they do happen, they provide dramatic evidence that Sagittarius A is not completely dormant. What causes these flares? Several theories compete, and the truth may involve multiple mechanisms operating under different conditions. One possibility involves magnetic field reconnection. In the turbulent accretion flow around the black hole, magnetic field lines get twisted and compressed until they become unstable. When they snap and reconfigure into lower energy configurations, the stored magnetic energy gets released suddenly, heating particles to extreme temperatures and causing them to emit synchrotron radiation. This process is analogous to solar flares on the Sun, where magnetic reconnection releases energy in spectacular eruptions. The pattern of intensity variations during some Sagittarius A flares resembles solar flare patterns supporting this hypothesis. Another explanation involves tidal disruption of objects falling toward the black hole. Asteroids or small planetary bodies venturing too close to Sagittarius A would be torn apart by tidal forces, the difference in gravitational pull between the near and far side of the object exceeding its structural strength. As the object disintegrates, its debris forms a temporary cloud of gas and dust that quickly heats up as it falls toward the event horizon. This heating could produce an X-ray flare. The energy release depends on the size of the disrupted object. A small asteroid might produce a modest flare. A larger body could create a mega flare. Some calculations suggest that objects the size of large asteroids, several kilometers across, could produce flares matching the brightest ones observed. A fascinating complication involves G2, a mysterious object that astronomers tracked as it approached Sagittarius A in the early 2010s. First noticed in 2002 and confirmed by detailed observations in 2012, G2 appeared to be a cloud of gas with about 3 times Earth's mass, moving on a trajectory that would bring it within 260 astronomical units of the black hole in early 2014. Many astronomers predicted that G2 would be torn apart by the black hole's tidal forces, with debris falling across the event horizon and triggering a massive brightening event as the infalling matter heated up and radiated. The encounter was expected to be spectacular, potentially the brightest flare from Sagittarius A in human history. It didn't happen. When G2 reached pericenter in May 2014, the predicted fireworks failed to materialize. The object emerged from its close encounter largely intact, somewhat stretched and distorted but not destroyed. Observations suggested that G2 might not have been a simple gas cloud after all. Instead, it appears to be a star surrounded by a dusty envelope. The star's gravity held the envelope together enough to survive the close pass. Another interpretation suggested that G2 is part of a continuous stream of gas, a denser clump within a flow of material that constantly feeds the black hole, so its passage didn't represent a sudden infall event, but rather a routine part of the accretion process. Interestingly, there was a surge in X-ray flares from Sagittarius A, starting in August 2014, a few months after G2's closest approach. Chandra observations showed a 2 to 3-fold increase in the rate of bright flares compared to the typical rate. Some researchers wondered whether this delayed response might be related to G2 after all. Perhaps some material was stripped from the object and took time to spiral inward and heat up. Or perhaps the encounter disturbed the accretion flow in ways that made flares more likely for a period afterward. The evidence remains ambiguous, and not all astronomers are convinced that the increased flaring had anything to do with G2. Another possibility, perhaps the most intriguing, is that flares are simply a normal property of weakly accreting black holes. Observations of other supermassive black holes with similar accretion rates to Sagittarius A show that they too exhibit long-term variations in their flaring properties. They have active periods with frequent bright flares and quieter periods with fewer events. Sagittarius A might undergo similar cycles. If true, the increased flare activity in 2014 and later might represent a natural variation in the black hole's behavior rather than a response to any specific external trigger. Infrared observations provide additional clues. The James Webb Space Telescope has observed Sagittarius A at infrared wavelengths, capturing both faint flickers and brighter flares over time periods of several hours. These infrared flares likely originate from synchrotron emission, radiation produced when high-energy electrons spiral through magnetic fields near the black hole. The electrons must be accelerated to relativistic speeds by some mechanism, possibly magnetic reconnection or shock waves in the accretion flow. The infrared emission varies on timescales as short as minutes, corresponding to orbital periods at just a few times the Schwarzschild radius. This means we're seeing processes occurring within about 100 million kilometers of the event horizon, incredibly close to the point of no return. Perhaps most dramatically, evidence suggests that Sagittarius A was far more active in the relatively recent past. In 2013, NASA's IKES-PE X-ray Observatory, combined with data from Chandra, revealed something unexpected. When astronomers looked at giant molecular clouds near the galactic center, clouds of cold hydrogen gas dozens of light years away from Sagittarius A, they saw these clouds glowing in X-rays. Cold gas shouldn't emit X-rays, but if the gas is illuminated by a powerful X-ray source, it can scatter and reflect those X-rays like a mirror. The molecular clouds near Sagittarius A were reflecting X-rays from a source that no longer exists, an echo from the past. By measuring the X-ray properties of the reflected light and accounting for the time delay, the light travel time from Sagittarius A to the cloud and then to Earth, astronomers concluded that the black hole underwent a massive outburst approximately 200 years ago. The luminosity during this outburst was about 1 million times stronger than the current X-ray emission from Sagittarius A, comparable to a moderate active galactic nucleus. For perhaps years or decades, our galaxy's center blazed with energy as the black hole consumed a substantial amount of matter. Then the fuel ran out or the feeding mechanism shut down, and Sagittarius A returned to its current, quiet state. This discovery suggests that the black hole's activity varies dramatically over timescales of centuries. What we observe today is just a snapshot of a system that can change drastically over human historical timescales. These flares and variations paint a picture of a black hole that's mostly quiet but not completely dormant. Sagittarius A consumes matter at a trickle, not a flood. Detailed observations using Chandra have shown that less than 1% of the material within the black hole's gravitational influence actually makes it to the event horizon. Most of the gas is too hot and moving too fast to fall in directly. It has too much angular momentum. Instead, the gas forms a thick, inefficient accretion flow that gradually loses energy and spirals inward. But along the way, much of the material gets ejected in winds and outflows, carrying energy away from the black hole. Only a small fraction, the coldest and densest clumps, manages to fall all the way in. This inefficiency explains why Sagittarius A is so dim despite having millions of solar masses of potential fuel surrounding it. If the accretion were efficient, the black hole would shine like a quasar. Instead, it's barely visible, a whisper of emission from the edge of oblivion. But those occasional flares remind us that the monster is still there, still feeding, still reshaping the galaxy around it in subtle ways. And one day, perhaps when the Milky Way collides with the Andromeda Galaxy in about 4 billion years, Sagittarius A might wake up in earnest. The collision will send huge amounts of gas flowing toward the galactic centres of both galaxies. The black holes, currently starved, will feast. Our galaxy's core might briefly become a quasar, outshining all the stars in both galaxies, visible halfway across the universe. But that's a story for the distant future. Understanding how Sagittarius A feeds, or rather how it fails to feed efficiently, requires diving into the physics of accretion. When matter falls toward a black hole, it doesn't plunge straight in like water down a drain. It has angular momentum, a tendency to orbit rather than fall. As a result, in falling matter forms an accretion disk, a swirling vortex of gas and dust that gradually spirals inward, losing angular momentum through friction and magnetic interactions. The disk is where matter meets its fate, where the energy of infall gets converted into radiation, and where the black hole's appetite is either satisfied or left wanting. For Sagittarius A, the accretion disk is surprisingly dim and sparse. Observations reveal a thin disk of hot gas extending outward from the black hole for several thousand Schwarzschild radii, perhaps 10 to 100 million kilometers. The gas temperature in the inner regions reaches millions of degrees Celsius, hot enough that the atoms are completely ionized into a plasma of free electrons and nuclei. At these temperatures, the gas glows in X-rays and infrared, radiation, but the amount of gas in the disk is small. Estimates suggest the total mass of material within the innermost stable orbit, the closest distance where matter can orbit without immediately falling in, is tiny, perhaps equivalent to a few Earth masses. That's nothing compared to the 4.3 million solar masses of the black hole itself. Why is there so little matter? The answer involves the interplay between gravity, heat, and angular momentum. Material in the galactic center region moves in complex orbits, influenced not just by the black hole, but by the gravitational pull of millions of nearby stars. This creates a chaotic environment where gas clouds collide, fragment, and exchange momentum. Some gas loses enough angular momentum to fall toward the black hole, but as it falls and compresses, it heats up dramatically. The thermal energy increases until the gas pressure becomes strong enough to partially resist further infall. The result is a thick, hot, slowly accreting flow rather than a thin, cool, rapidly accreting disk. This type of accretion flow is called a radiatively inefficient accretion flow, or SHIOS-AF. In a standard thin disk, matter spirals inward efficiently, radiating away most of its gravitational potential energy before crossing the event horizon. The system is bright and efficient at converting mass into radiation, but in a RAF the hot gas doesn't cool effectively. It can't radiate away its energy fast enough. Instead, most of the thermal energy gets advected, carried along with the gas as it falls into the black hole. The black hole ends up consuming energy as well as mass, and the system is much dimmer than a standard disk would be. Observations with Chandra X-ray Observatory have provided crucial insights into this inefficient feeding process. By monitoring Sagittarius A continuously for 5 weeks in 2012, astronomers captured an unprecedented detailed view of the accretion flow. They found that the material near the event horizon is incredibly dilute and hot, with temperatures exceeding 10 million degrees. The density is so low that particles can travel relatively large distances before colliding with each other. Under these conditions, the gas can't settle into a thin disk. It remains puffed up in a thick, turbulent structure. Moreover, Chandra observations reveal that significant outflows occur. Gas that approaches the black hole doesn't necessarily fall in. Much of it gets accelerated outward, ejected back into the surrounding environment. This happens because the accretion flow is unstable. Magnetic fields threading the gas can extract energy and angular momentum, flinging material away from the black hole in winds and jets. Calculations suggest that for every unit of mass that crosses the event horizon, 99 units get ejected before reaching the point of no return. This 99% rejection rate explains why Sagittarius A accretes so slowly and shines so dimly. The ejected material carries energy away from the black hole, depositing it into the surrounding region. This feedback process has profound implications for galaxy evolution. In many galaxies, the central supermassive black hole's outflows and jets regulate star formation in the galactic core. They heat the gas too much for it to collapse and form stars, creating a self-regulating cycle where the black hole suppresses its own fuel supply. For Sagittarius A, the effect is modest because the black hole is so underluminous. But in more active galaxies with powerfully accreting black holes, feedback can completely shut down star formation in the central regions, sculpting the galaxy's structure. The accretion flow around Sagittarius A also shows intriguing variability on short timescales. The gas orbits the black hole with periods of minutes near the innermost stable orbit. During these orbits, clumps and hotspots in the plasma emit radiation that varies as they circle around. By watching these variations, astronomers can trace the orbital motion directly. In 2018, using the gravity instrument on the Very Large Telescope in Chile, astronomers detected clumps of gas moving at 30% of light speed in tight orbits around Sagittarius A. These observations showed emission from hotspots executing complete orbits in about 45 minutes, directly measuring the motion of matter just outside the event horizon. These hotspots produce the bright flares observed in infrared and X-ray wavelengths. They appear to be localized regions where magnetic field lines reconnect, or where shocks in the accretion flow compress and heat the gas to even higher temperatures. The hotspot emits synchrotron radiation as energetic electrons spiral through the magnetic field. As the spot orbits the black hole, the radiation we see varies in brightness and color due to relativistic beaming effects and gravitational lensing. When the hotspot moves toward us, its light appears brighter and blue shifted. When it moves away, the light dims and red shifts. By carefully analyzing these variations, astronomers can map the structure of the accretion flow and measure the spin of the black hole. Speaking of spin, recent studies using Event Horizon Telescope data have attempted to measure Sagittarius A's spin. Black holes are characterized by just two properties: mass and spin. The spin describes how fast the black hole rotates, or more accurately, how much angular momentum it contains. A non-rotating black hole is described by the Schwarzschild solution to Einstein's equations. A rotating black hole is described by the more complex Kerr solution. Rotation matters because it drags space-time around with it, creating effects like frame dragging that influence the orbits of nearby matter. Preliminary results suggest that Sagittarius A is spinning, though not at the maximum rate possible. The spin is likely moderate, perhaps 30 to 60% of the maximum value. This spin probably resulted from the black hole's formation and growth history. If the black hole formed from the collapse of a massive gas cloud, it would inherit the cloud's angular momentum. If it grew primarily by accreting gas from a preferred direction, the accretion would spin it up over time. If it grew by merging with other black holes from random directions, the mergers might cancel out some of the spin. Recent work from researchers at the University of Nevada, Las Vegas suggests that Sagittarius A might have formed from a merger of two smaller supermassive black holes approximately 9 billion years ago. The spin misalignment observed could be evidence of this violent past. The magnetic fields threading the accretion flow are another critical component. Polarized light observations from the Event Horizon Telescope reveal strong organized magnetic fields spiraling around the black hole, similar to those seen in M87. These fields likely play a central role in channeling gas into the accretion flow and in driving the outflows that reject most of the material. The magnetic field structure appears remarkably similar between Sagittarius A and M87, despite the enormous difference in black hole mass and galaxy type. This suggests that magnetic fields around supermassive black holes follow universal patterns, governed by the same physical processes regardless of scale. Understanding the accretion flow is critical not just for Sagittarius A, but for all supermassive black holes. These objects regulate galaxy evolution, influence star formation, and may seed the formation of cosmic structure through their gravitational influence. By studying our nearest supermassive black hole in exquisite detail, we gain insights into how these cosmic monsters operate throughout the universe. And we're reminded that despite their fearsome reputation, black holes are selective eaters, rejecting far more than they consume, leaving the surrounding galaxy largely untouched while they wait for their next substantial meal. How did Sagittarius A form? This question leads into one of the deepest mysteries in astrophysics. We understand how stellar mass black holes form. A massive star exhausts its nuclear fuel, its core collapses, and if enough mass remains, the collapse continues past the neutron star stage into a black hole. Simple. Well, not simple, but at least we have a clear physical mechanism. Supermassive black holes are different. No star is massive enough to collapse directly into a 4 million solar mass black hole. There must be another explanation, and despite decades of research, astronomers still don't have a definitive answer. One possibility is that supermassive black holes grow from smaller seeds. Perhaps stellar mass black holes, formed from the first generation of stars in the early universe, acted as gravitational anchor points. Gas in their vicinity would fall in, slowly increasing their mass. Given enough time, a 100 solar mass stellar black hole could grow to 1 million solar masses or more. But there's a problem with this scenario: time. Observations of distant quasars show that supermassive black holes with billions of solar masses existed when the universe was less than 1 billion years old. That's not enough time for a stellar mass black hole to grow through gradual accretion, even if the black hole accreted at the maximum possible rate, a limit called the Eddington limit, where radiation pressure from the infalling matter balances gravity and prevents further infall. It would take hundreds of millions of years to reach 1 billion solar masses starting from a stellar mass seed. To solve this timing problem, astronomers have proposed several alternatives. One idea involves population 3 stars, the first generation of stars that formed from pristine hydrogen and helium gas shortly after the Big Bang. Without heavier elements to help them cool and fragment, these primordial gas clouds may have collapsed into extraordinarily massive stars, perhaps hundreds or even thousands of times the Sun's mass. When such a star exhausted its fuel and collapsed, it could have formed an intermediate mass black hole of thousands of solar masses, providing a much larger seed for subsequent growth. These intermediate mass seeds would need less time to reach supermassive scales through accretion. Another proposal is the direct collapse scenario. Under the right conditions, a massive gas cloud in the early universe could have collapsed directly into a black hole without forming stars first. This would require the cloud to remain hot enough to avoid fragmenting into smaller star-forming clumps, while also being dense enough to collapse under its own gravity. Certain environments in the early universe might have provided these conditions, perhaps in regions flooded with ultraviolet radiation from nearby galaxies that kept the gas ionized and hot. If direct collapse occurred, it could have produced black holes of 10,000 to 100,000 solar masses right from the start, dramatically reducing the time needed to grow to supermassive scales. A third mechanism involves hierarchical mergers. If many smaller black holes formed in the early universe, they would gradually sink to the centers of forming galaxies through a process called dynamical friction. Once there, they would merge with each other. Two 1,000 solar mass black holes merging create a 2,000 solar mass black hole. That black hole merges with another, creating a 4,000 solar mass black hole, and so on. Through repeated mergers, the black hole mass can grow exponentially. This mechanism can work faster than accretion because it doesn't rely on capturing gas, only on the galaxy's dynamical evolution bringing black holes together. For Sagittarius A specifically, recent research has provided intriguing clues about its formation history. A 2024 study by researchers at the University of Nevada, Las Vegas analysed the spin properties and orientation of Sagittarius A using Event Horizon Telescope data. They found that the black hole's spin axis is significantly misaligned with the angular momentum axis of the Milky Way galaxy. In a simple formation scenario where the black hole grew smoothly from a single seed by accreting gas from the galactic disk, the spin and disk should be aligned. The observed misalignment suggests a more violent history. The UNLV team concluded that the most likely explanation is a major merger. Sagittarius A probably formed from the collision and coalescence of two smaller supermassive black holes, likely with a mass ratio of about 4:1, approximately 9 billion years ago. This merger would have occurred during the early assembly of the Milky Way, when smaller galaxies merged together to form our galaxy. Each small galaxy would have carried its own central black hole. When the galaxies merged, their black holes spiraled toward each other through dynamical friction, eventually merging in a cataclysmic event that released enormous energy in gravitational waves. The merger process is incredibly violent. As two black holes orbit each other, they emit gravitational waves, ripples in space-time that carry energy away from the system. This energy loss causes the orbits to shrink. The black holes spiral closer and closer, orbiting faster and faster until they finally merge in a fraction of a second. The resulting black hole vibrates like a struck bell, emitting powerful gravitational waves before settling into a stable configuration. The final spin of the merged black hole depends on the spins and orbital properties of the progenitors. A merger can produce a rapidly spinning black hole if the orbital angular momentum adds constructively to the spins, or a slowly spinning black hole if the angular momentum subtracts. The misalignment of Sagittarius A's spin with the galactic plane suggests that the merger occurred between black holes whose orbital plane was tilted relative to the galaxy's rotation. This could happen if one of the progenitor black holes came from a satellite galaxy falling into the Milky Way from an inclined orbit. The merger would have been a spectacular event. For a brief period, Sagittarius A would have emitted gravitational waves detectable across the universe by future space-based gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, scheduled for launch in the 2030s. LISA will detect mergers of supermassive black holes throughout cosmic history, and the statistical properties of those mergers will test whether hierarchical merging is indeed the dominant formation mechanism. After the merger, Sagittarius A continued growing through accretion. Over the subsequent 9 billion years, it has accumulated additional mass by consuming gas and dust from the galactic center region, and by capturing stars that ventured too close. But the growth has been slow. The black hole's current mass is only 4.3 million solar masses. If it had been actively feeding this entire time, it could be far more massive. The modest mass suggests that Sagittarius A has been starved for most of its existence, only occasionally experiencing periods of enhanced accretion when gas-rich galaxies merged with the Milky Way, or when tidal interactions funneled gas toward the center. This formation history makes Sagittarius A a relatively typical supermassive black hole by mass standards. While not as massive as the monsters in giant elliptical galaxies, it's comparable to the central black holes in many spiral galaxies. This typicality is fortunate for astronomers because it means Sagittarius A represents a common class of supermassive black holes, making observations of it broadly applicable to understanding black holes throughout the universe. The challenge now is to refine our understanding of the formation process, to determine what fraction of supermassive black holes formed through direct collapse versus hierarchical merging, and to understand how the formation mechanism influences the subsequent evolution of both the black hole and its host galaxy. Sagittarius A doesn't just sit passively at the galactic center. Its enormous mass influences the entire Milky Way galaxy, serving as a gravitational anchor around which everything orbits. Our Sun, for instance, orbits the galactic center at a distance of roughly 26,000 light-years, completing one full orbit every 225 to 250 million years. This orbital period is sometimes called a cosmic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. We're currently somewhere in the middle of our 21st cosmic year. The Sun's orbital velocity is approximately 220 kilometers per second, about 490,000 miles per hour. This might sound fast, but it's slow compared to stars closer to the galactic center, which must move faster to resist the stronger gravitational pull from Sagittarius A and the dense concentration of stars surrounding it. The S-stars we discussed earlier, orbiting within light days or light hours of the black hole, reach several percent of light speed. Even at thousands of light years away, stars orbit significantly faster than the Sun. The orbital velocity as a function of distance provides a direct measurement of how mass is distributed in the galaxy, and those measurements confirm that a concentrated mass of millions of solar masses occupies the galactic center. But Sagittarius A's influence extends beyond simply being the gravitational center. The black hole affects the structure of the galaxy in subtle ways. When the black hole accretes matter and produces energetic outflows, those outflows deposit energy into the surrounding gas. This heating can suppress star formation in the galactic center region. Observations show that despite the high density of gas near the galactic center, star formation is less efficient there than in the galactic disk where our Sun resides. The black hole's feedback, even though currently weak, may play a role in this suppression. Over the galaxy's history, Sagittarius A has probably gone through periods of much higher activity. Galaxy mergers and close encounters with satellite galaxies can funnel large amounts of gas toward the galactic center, triggering bursts of accretion. During these episodes, Sagittarius A would briefly become an active galactic nucleus, shining with the power of billions of suns. The intense radiation and powerful jets or winds from such an event would heat the surrounding gas over huge volumes, perhaps thousands of light years, preventing that gas from cooling and forming stars for millions of years afterward. This feedback mechanism is thought to be one of the key processes regulating galaxy growth throughout the universe. The discovery of the 200-year-old outburst mentioned earlier provides a glimpse into these active periods. If Sagittarius A was 1,000,000 times brighter 2 centuries ago, it was temporarily in a low-luminosity active state. The energy released during that event would have illuminated the entire galactic center region, potentially affecting gas clouds and star-forming regions over light-year scales. The fact that this happened so recently in cosmic terms suggests that such events are relatively common on human historical timescales, even if they appear rare from our limited observational baseline. Looking forward, Sagittarius A's future is intimately tied to the Milky Way's fate. The most dramatic change will occur in approximately 4 billion years when the Milky Way and Andromeda galaxies collide. This event has been inevitable since both galaxies formed. They're moving toward each other at about 110 kilometers per second, and their mutual gravity ensures they will eventually merge. Despite the name collision, the merger will be a relatively gentle process for individual stars. Galaxies are mostly empty space. The chance of any star colliding with another star during the merger is negligible, but the gas clouds in both galaxies will collide spectacularly, compressing and heating as they crash together. The gravitational stirring during the merger will funnel enormous amounts of gas toward the centers of both galaxies. Sagittarius A and Andromeda's central black hole, which contains about 200 million solar masses, will both experience massive feeding frenzies. For perhaps millions of years, both black holes will shine as quasars, each outshining all the stars in their respective galaxies. The radiation from the active black holes will be so intense that it could sterilize planets over much of both galaxies, rendering them temporarily uninhabitable. This will be one of the most energetic periods in the merged galaxy's history. Eventually, after the initial chaos of the merger settles, the two black holes themselves will merge. They'll spiral toward each other, over hundreds of millions of years through dynamical friction, eventually forming a binary black hole system at the center of the merged galaxy. The binary will emit gravitational waves, shrinking the orbit until the black holes coalesce in a final merger that will send ripples through space-time detectable across the universe. The resulting black hole will contain about 204 million solar masses, nearly 50 times more massive than Sagittarius A is today. This merged black hole will then govern the center of the new galaxy, sometimes called Milkomeda or Milkdromeda, continuing the cycle of occasional feeding and long periods of quiescence. On much longer timescales, trillions of years into the future, Sagittarius A and its merged descendant will continue growing slowly through stellar captures and rare accretion events. Eventually, as stars in the galaxy exhaust their fuel and die, the galaxy will darken. Fewer and fewer stars will remain, and the black hole's environment will become increasingly barren. The black hole will persist long after the last stars have died, a cold, dark remnant in an aging universe. And on timescales so long they're almost meaningless, perhaps 10 to the 100 years or more, even the black hole will evaporate through Hawking radiation, quantum mechanical processes at the event horizon that slowly convert the black hole's mass into radiation. But that's so far in the future that the universe itself will be almost unrecognizable. For now, in the present epoch, Sagittarius A serves as the gravitational anchor and occasional energetic heartbeat of our galaxy. Everything in the Milky Way orbits it, from the central stellar cluster to the outermost halo stars hundreds of thousands of light years away. We're all passengers on a cosmic merry-go-round, spinning around a black hole we cannot see, held in place by gravity we cannot escape, living our brief lives in the long shadow of the monster at the center. Sagittarius A isn't just an astronomical curiosity, it's a physics laboratory unlike anything we can create on Earth. The conditions near its event horizon probe regimes of gravity and space-time curvature that test the limits of general relativity and potentially reveal new physics beyond Einstein's century-old theory. Every observation of matter and light near the black hole is an experiment in extreme physics, a chance to verify or falsify our most fundamental theories about how the universe works. One of the key tests involves gravitational redshift, which we discussed earlier in the context of the S2 star observations. But the effect goes beyond just stars. Light emitted from gas in the accretion disk also experiences gravitational redshift. Photons climbing out of the black hole's gravitational well lose energy, shifting to longer wavelengths and lower frequencies. The closer to the event horizon the emission occurs, the stronger the redshift. By measuring the spectrum of light from different parts of the accretion flow, astronomers can map the strength of the gravitational field and confirm that it matches general relativity's predictions. Another relativistic effect is frame dragging, also called the lens-Thirring effect. A rotating black hole literally drags space-time around with it. Anything orbiting the black hole gets pulled along by this dragging effect, causing orbits to precess in the direction of the black hole's rotation. The effect is strongest close to the event horizon and decreases with distance. For Sagittarius A, frame dragging influences the motion of gas in the inner accretion flow and potentially affects the orbits of the closest approaching S-stars. Measuring frame dragging precisely requires extremely high-precision astrometry, but future observations with improved instruments may detect it. Time dilation is another consequence of strong gravity. Clocks run slower in gravitational fields, and the effect is dramatic near a black hole. For an observer watching from far away, time appears to slow down for objects approaching the event horizon, asymptotically stopping as they reach the horizon itself. But for an infalling object, time proceeds normally from its own perspective. It crosses the horizon in finite proper time and quickly reaches the central singularity. This difference between coordinate time and proper time is one of the strange features of relativity that still challenges intuition even after a century of the theory. The event horizon itself represents a boundary in space-time with profound implications. It's not a physical surface you could touch. It's a mathematical boundary defined by the property that light emitted from inside cannot escape to infinity. The location of the horizon depends on the black hole's mass and spin. For a non-rotating black hole, the horizon is a sphere called the Schwarzschild radius. For a rotating black hole, the situation is more complex. The horizon is no longer perfectly spherical, and there's an additional boundary called the ergosphere, where objects cannot remain stationary even if they're outside the event horizon. They get dragged around by the black hole's rotation, forced to co-rotate with it. Inside the event horizon lies the singularity, a point where space-time curvature becomes infinite, and general relativity breaks down. At the singularity, the known laws of physics cease to apply. Density becomes infinite. Tidal forces become infinite. The singularity is hidden behind the event horizon, protected from outside view by what physicist Roger Penrose called cosmic censorship, the idea that nature forbids naked singularities that could be observed from the outside universe. The singularity remains forever hidden, its secrets locked away behind the event horizon. Or do they? Quantum mechanics suggests that black holes aren't completely black. In the 1970s, physicist Stephen Hawking showed that quantum effects near the event horizon allow black holes to emit radiation, now called Hawking radiation. The mechanism involves virtual particle-antiparticle pairs that constantly pop into existence near the horizon. Usually these pairs annihilate almost immediately, but if one particle falls into the black hole while the other escapes, it appears to an outside observer as if the black hole emitted a particle. This process slowly drains energy from the black hole, causing it to evaporate over immensely long timescales. For Sagittarius A, the Hawking radiation is utterly negligible. The temperature of the radiation is about 10 to the minus 14th Kelvin, far colder than the cosmic microwave background radiation filling the universe. In fact, Sagittarius A is currently growing, not shrinking, because it absorbs more energy from the cosmic microwave background than it emits through Hawking radiation. Only after the universe has expanded and cooled for trillions of times its current age, long after all stars have died and the cosmic microwave background has cooled to nearly absolute zero, will black holes begin to evaporate through Hawking radiation. Even then, a black hole of Sagittarius A's mass will take 10 to the 90 years or more to completely evaporate. That's a 1 followed by 90 zeros, a timescale so long it makes the current age of the universe, a mere 14 billion years, seem like an eye blink. The photon sphere, the region where light can orbit the black hole, creates the shadow we see in event horizon telescope images. photons approaching the black hole on certain trajectories get captured into circular orbits just outside the event horizon. These orbits are unstable. Any small perturbation sends the photon either spiraling into the black hole or escaping to infinity. But for the brief moment they orbit, they create a bright ring around the shadow. The size of this photon ring depends only on the black hole's mass and spin, making it a fundamental probe of the black hole's properties. Gravitational lensing is another dramatic effect. The black hole's gravity bends light passing nearby, acting like a lens. Light from stars or gas behind the black hole gets deflected around it, potentially creating multiple images of the same object. In event horizon telescope images, we see light from gas on the far side of the black hole bent around and toward us, making the bright ring appear brighter on the side moving toward us due to a combination of lensing and relativistic beaming. These lensing effects confirm general relativity's predictions about how gravity bends light, extending tests of the theory into the strong field regime where Newtonian gravity completely fails. The behavior of matter at the event horizon connects to fundamental questions in quantum gravity, the hypothetical theory that would unite general relativity with quantum mechanics. These two pillars of modern physics are famously incompatible. General relativity describes gravity as the curvature of smooth, continuous spacetime. Quantum mechanics describes the universe as fundamentally discrete and probabilistic. Combining them has been one of the great unsolved problems in theoretical physics for nearly a century. Black holes are where this incompatibility becomes critical. At the singularity, quantum effects should dominate, but general relativity predicts infinite curvature. Something must give. String theory, loop quantum gravity, and other proposed theories of quantum gravity attempt to resolve this by providing a description of spacetime at scales smaller than the Planck length, about 10 to the minus 35 meters. At these scales, spacetime itself might become discrete or foamy, eliminating the singularity and replacing it with some more complex structure. But we have no observational evidence for any of these theories yet. They remain speculative. Sagittarius A might help change that. If quantum gravity effects modify the structure near the event horizon in detectable ways, observations of matter and light in that region could reveal the signatures. This is a long shot. The quantum gravity scale is so small that even at the event horizon of a supermassive black hole, quantum effects are likely swamped by classical general relativistic effects. But some theorists have proposed that echoes or other anomalies in gravitational wave signals from black hole mergers, or in the dynamics of matter near event horizons, might betray quantum gravity. Future observations with improved instruments might detect such signatures. For now, Sagittarius A serves as an exquisite laboratory for testing general relativity in its domain of validity, the classical strong field regime. Every measurement confirms Einstein's equations with greater and greater precision. The stellar orbits match predictions. The gravitational redshift matches predictions. The shadow size matches predictions. The relativistic beaming and lensing effects match predictions. After more than a century, general relativity remains undefeated, an elegant mathematical theory that captures the nature of gravity with stunning accuracy across scales from planetary orbits to black holes. But physics is never finished. There are always deeper questions, more extreme regimes to test. Sagittarius A represents our best opportunity in the foreseeable future to push these tests as far as current technology allows, and perhaps, just perhaps, it will surprise us with something unexpected, a deviation from general relativity, a hint of new physics, a clue to the quantum nature of gravity. That's the hope that drives astronomers to build better telescopes, to develop more sophisticated analysis techniques, to squeeze every last drop of information from the faint light reaching us from the edge of oblivion. Sagittarius A doesn't live in isolation. The galactic center is one of the most densely packed regions in the Milky Way, a cosmic metropolis where stars crowd together thousands of times more densely than in our solar neighborhood. Within the central parsec, about 3 light-years, roughly 100,000 stars orbit the black hole. Many of these are ordinary main-sequence stars, burning hydrogen steadily like our Sun. Others are evolved giants and supergiants, stars that have exhausted their core hydrogen and swollen to enormous sizes. And sprinkled among them are exotic objects, neutron stars, stellar mass black holes, white dwarfs, and even a magnetar. The presence of stellar mass black holes near Sagittarius A was confirmed in 2018 when researchers analysed X-ray emissions from the galactic centre. They found evidence for thousands of stellar mass black holes, each 10 to 100 solar masses, orbiting within 3 light-years of the supermassive black hole. This population isn't surprising theoretically. Stars near the galactic centre formed from gas with higher metallicity than in the outer galaxy, and massive metal-rich stars are more likely to form stellar mass black holes when they die, rather than exploding completely as supernovae. Over billions of years, these stellar corpses have accumulated near the galactic centre through a process called mass segregation. More massive objects sink toward the centre of a stellar cluster due to dynamical friction, while lighter objects get scattered to larger distances. Having thousands of black holes within a few light-years creates an incredibly hazardous environment. These black holes occasionally interact gravitationally with each other and with passing stars. Close encounters can fling objects out of the cluster at high speeds, or, more rarely, result in collisions and mergers. When two stellar mass black holes merge, they emit gravitational waves. The LIGO and Virgo gravitational wave observatories have detected dozens of such mergers across the universe. Some of these events might originate from dense environments like the galactic centre, though distinguishing galactic centre mergers from those occurring in other environments is challenging. The magnetar discovered near Sagittarius A adds another layer of intrigue. Magnetars are neutron stars with extraordinarily strong magnetic fields, perhaps 1,000 trillion times stronger than Earth's magnetic field. These magnetic fields are so intense they distort the star's crust, causing starquakes that trigger bursts of X-rays and gamma rays. The magnetar near Sagittarius A, designated SGR J-Santis van Voorfilser 2000, underwent an outburst in 2013 that made it temporarily the brightest X-ray source in the galactic centre region, outshining even Sagittarius A itself. The magnetar sits only about 3 light seconds from the black hole, closer than the orbit of Saturn in our solar system. At that distance, it experiences the black hole's gravity strongly, though not strongly enough to be pulled in immediately. Observations of the magnetar's X-ray pulsations allow astronomers to measure its spin and magnetic field with high precision. The magnetic field is about 10 to the 14 Gauss, among the strongest ever measured. The magnetar is also moving through a wind of particles from the black hole's accretion flow. This interaction between the magnetar's magnetic field and the black hole's environment creates unique physical conditions that don't exist anywhere else in the universe. The overall stellar environment near Sagittarius A is extraordinarily violent by cosmic standards. Stars pass close to each other regularly on astronomical timescales. Some of these encounters result in collisions. When two stars collide in the dense galactic centre environment, they can merge into a single more massive star or disrupt each other entirely, scattering stellar material across the region. Stellar collisions might explain some of the unusual stars observed near the black hole, stars that appear younger than they should be, based on the environment's age. Another hazard involves tidal disruption events. When a star passes too close to the black hole, tidal forces pull it apart. The near side of the star experiences stronger gravity than the far side, stretching the star into a long filament. If the tidal force exceeds the star's self-gravity, the star disintegrates. About half the stellar debris falls into the black hole, heating up as it spirals inward and producing a bright flare lasting weeks to months. The other half gets flung out at high velocity, escaping the system entirely. Tidal disruption events are rare at Sagittarius A because the black hole is relatively small. Larger black holes have event horizons so large that tidal forces near the horizon are weak, allowing stars to cross intact. But for a 4 million solar mass black hole, a sun-like star gets disrupted well outside the horizon. Astronomers have searched for evidence of past tidal disruption events near Sagittarius A by looking for unusual stellar remnants and streams of debris. Some candidates have been found, though confirming them requires careful analysis. The overall rate of tidal disruptions at Sagittarius A is estimated to be about 1 every 10,000 to 100,000 years, so catching one in real time would be extraordinarily lucky. But if it happened, it would provide an unprecedented opportunity to study how stars are destroyed by black holes and how the debris evolves. The presence of young, massive stars very close to Sagittarius A is itself a puzzle. These stars are only a few million years old, far younger than the typical stars in the galactic bulge. They shouldn't be there because star formation near a supermassive black hole should be inhibited by tidal forces, yet there they are, orbiting within fractions of a light year of the event horizon. The leading explanation is that these stars formed farther out, in a region where star formation is possible, and then migrated inward through dynamical interactions with other stars. Alternatively, they might have formed in a dense gas disk around the black hole during a past episode of high accretion, though this scenario requires special conditions. These young stars won't last forever in their current orbits. Over millions of years, gravitational interactions with other stars will perturb their orbits, either flinging them outward to larger distances or sending them plunging into the black hole. Some will undergo close encounters with Sagittarius A and get ejected from the galactic centre entirely at velocities high enough to escape the Milky Way. These hypervelocity stars have been detected leaving the galaxy at speeds exceeding 1,000 kilometers per second. Tracing their orbits backward suggests some originated near the galactic centre, flung out by close encounters with the black hole. This crowded, violent environment makes the galactic centre a unique laboratory for studying stellar dynamics under extreme conditions. Nowhere else in the Milky Way do stars move so fast, orbit so close to a supermassive black hole, or interact so frequently with exotic compact objects. Every observation of this region adds to our understanding of how matter behaves in the strongest gravitational fields nature can produce short of the event horizon itself. The dense stellar population also creates an environment rich in stellar winds and supernova remnants. Massive stars near the black hole go through their life cycles relatively quickly, perhaps 10 to 50 million years from birth to death. When they explode as supernova, they inject enormous amounts of energy and heavy elements into the surrounding gas. These explosions create expanding shells of hot gas that sweep through the region, compressing nearby gas clouds and potentially triggering new rounds of star formation. The X-ray observations of the galactic centre show multiple supernova remnants overlapping each other, creating a complex web of shocked gas and high-energy particles. These supernova remnants interact with Sagittarius A's accretion flow in complex ways. Some of the ejected material eventually falls back toward the black hole, contributing to the pool of gas available for accretion. Other material gets accelerated to high velocities by the supernova blast wave and escapes the central region entirely. The net effect is a constant churn of matter, with material being deposited, processed, and ejected in cycles that span thousands to millions of years. Stellar winds from massive stars also contribute significantly to the gas supply near the black hole. Young, hot stars blow powerful winds, streams of particles that flow away from the star at hundreds to thousands of kilometers per second. In the dense galactic center environment, these winds from multiple stars collide with each other, creating shock fronts where the gas heats to millions of degrees and emits X-rays. The cumulative effect of stellar winds from the entire stellar cluster supplies a steady flow of gas toward the central region, though most of this gas is too hot and has too much angular momentum to fall into the black hole directly. There's also the phenomenon of evaporation. Stars passing very close to the black hole but not close enough to be disrupted tidally can still lose material. The intense gravitational gradient creates differential forces across the star that heat its outer layers. Over many close passages, these layers can be gradually stripped away, feeding the black hole while slowly eroding the star. This process is subtle and takes a long time, but for stars with orbits that repeatedly bring them within a few hundred astronomical units of Sagittarius A, it could be significant over millions of years. The gravitational interactions between stars in this crowded environment also lead to interesting dynamical effects. Stars exchange energy and angular momentum through close encounters, with some gaining enough energy to be ejected from the cluster, while others sink deeper toward the black hole. This dynamical evolution creates a mass-segregated structure where the most massive objects concentrate in the very center. Over time, this process builds up the population of stellar mass black holes and neutron stars very close to Sagittarius A, creating conditions ripe for interesting interactions and mergers. Binary star systems in the galactic center face particular challenges. The tidal field from Sagittarius A and the high density of stars make binaries vulnerable to disruption. A close encounter with a passing star or the black hole's tidal forces can tear binary systems apart, leaving their component stars on separate trajectories. Alternatively, binaries that survive can have their orbits dramatically altered, potentially becoming more tightly bound or having their orbital planes reoriented. Some of the unusual stellar orbits observed might be explained by former binary stars that were disrupted. The radiation environment near Sagittarius A adds another dimension to the extreme conditions. During active periods or flares, the black hole emits intense X-rays and ultraviolet radiation that bathes the surrounding region. This radiation can photoionize gas in nearby molecular clouds, heat stellar atmospheres, and potentially affect the surface conditions of any planets orbiting nearby stars. While we haven't detected planets in the galactic center, they could exist, and their environments would be profoundly influenced by proximity to the supermassive black hole. Cosmic rays, high-energy particles accelerated to nearly light speed, are also abundant near the galactic center. Some of these cosmic rays are accelerated in supernova remnants. Others might be accelerated in the accretion flow around Sagittarius A, or in the interactions between stellar winds. The cosmic ray density near the black hole far exceeds that in the solar neighborhood, creating a harsh radiation environment that would be challenging for any form of life to survive. All these factors combine to make the galactic center one of the most energetic and dynamic regions in the Milky Way. It's a place of extremes where stars are born and destroyed on relatively short timescales, where black holes lurk by the thousands, where radiation and particles reach intensities found nowhere else in our galaxy. Understanding this environment requires observations across the entire electromagnetic spectrum, from radio waves to gamma rays, each wavelength revealing different aspects of the complex physics at work. And at the center of it all sits Sagittarius A, the gravitational anchor and ultimate destination for any matter that ventures too close to its domain. Sagittarius A isn't just important for understanding our own galaxy, it serves as a crucial benchmark for understanding supermassive black holes throughout the universe. Nearly every large galaxy appears to harbor a supermassive black hole at its center, ranging from millions to tens of billions of solar masses. These cosmic monsters play fundamental roles in galaxy evolution, regulating star formation, driving powerful jets and winds, and influencing the distribution of matter across cosmic scales. By studying Sagittarius A in exquisite detail, we gain insights that apply to black holes billions of light years away. The relationship between a galaxy and its central black hole is one of the most intriguing discoveries in modern astrophysics. Observations reveal a tight correlation between black hole mass and various properties of the host galaxy, particularly the mass of the galactic bulge, the spherical concentration of stars at the galaxy's center. Galaxies with more massive bulges harbor more massive central black holes, with the black hole mass typically about 1/1000th of the bulge mass. This correlation holds across enormous ranges of mass and galaxy type, from dwarf galaxies with black holes of millions of solar masses to giant elliptical galaxies with black holes of billions of solar masses. This correlation is remarkable because the black hole, despite its immense mass, is utterly tiny compared to the galaxy. Sagittarius A's event horizon is 12 million kilometers across. The Milky Way's bulge extends for thousands of light years, roughly 10 to the 20 times larger. Yet somehow, these two vastly different scales are intimately connected. The black hole contains less than 1/1000th of 1% of the galaxy's total mass, yet its presence shapes the entire galactic structure. The explanation involves feedback. When a supermassive black hole accretes matter vigorously, it becomes an active galactic nucleus, or AGN, shining with tremendous luminosity. The radiation, jets and winds from an AGN deposit enormous energy into the surrounding gas, heating it and driving it away from the galaxy's central regions. This suppresses star formation because hot gas cannot cool and collapse to form new stars. Over time, the AGN self-regulates its own growth. It heats the gas too much for it to fall in and feed the black hole further. The system reaches an equilibrium where the black hole mass correlates with the galaxy's properties. Sagittarius A fits this paradigm but represents an extreme case of quiescence. Most supermassive black holes with similar masses are far more luminous, either because they're actively accreting or because they went through active phases recently. Sagittarius A's extreme faintness makes it unusual and valuable for study. We're observing a black hole in its natural quiet state, not illuminated by a bright accretion disk that outshines the surrounding environment. This allows us to see details of the stellar population and gas distribution near the black hole that would be invisible if the black hole were actively feeding. Comparing Sagittarius A with other well-studied supermassive black holes reveals both universality and diversity in how these objects behave. The black hole at the centre of the galaxy M87, designated M87, is perhaps the most famous comparison. At 6.5 billion solar masses, M87 is over 1,500 times more massive than Sagittarius A. It sits in a giant elliptical galaxy 53 million light-years away, one of the largest galaxies in the nearby universe. Despite these enormous differences in mass, distance, and galaxy type, the Event Horizon Telescope images of both black holes look remarkably similar. Bright asymmetric rings surrounding dark shadows, with the shadow size proportional to the black hole mass. This similarity validates general relativity. Einstein's equations predict that all black holes, regardless of mass, have the same basic structure defined only by mass and spin. A 4 million solar mass black hole should look just like a 6 billion solar mass black hole when scaled appropriately. The Event Horizon Telescope observations confirm this prediction. The shadow-to-mass ratio is the same for both black holes within measurement uncertainties. The bright ring morphology is similar. The gravitational lensing effects match theoretical predictions. Black holes are indeed universal objects, their properties determined solely by mass and spin, not by how they formed or where they live. But there are also important differences between the two black holes that reveal how environment matters. M87 drives a powerful relativistic jet, a narrow beam of plasma shooting away from the black hole at nearly light speed, extending for thousands of light-years into intergalactic space. This jet is visible at radio, optical, and X-ray wavelengths, powered by the black hole's rotation and magnetic fields. Sagittarius A, by contrast, shows no evidence of a persistent jet. If it has jets at all, they're weak and transient, visible only during occasional flares. This difference likely reflects the accretion rate. M87 accretes more matter than Sagittarius A, maintaining a more substantial magnetized accretion flow, capable of launching and sustaining jets. The galaxy types also matter. M87 is an elliptical galaxy, formed through mergers of smaller galaxies over billions of years. Its central region is dominated by old stars and hot ionized gas, with little ongoing star formation. The Milky Way is a spiral galaxy with active star formation in its disk and a more complex environment. These differences in galaxy properties influence the supply of gas available to feed the central black hole. M87's hot gas halo provides a steady supply of material flowing toward M87. The Milky Way's cooler, clumpier environment provides less steady feeding to Sagittarius A, explaining its lower luminosity. Another fascinating comparison involves the black hole in the galaxy NGC 1277, located about 220 million light-years away. This black hole contains a staggering 17 billion solar masses, nearly 40% of the galaxy's total stellar mass. This vastly exceeds the typical black hole-to-bulge mass ratio, making NGC 1277's central black hole one of the most overmassive known. The galaxy itself is compact and dense, suggesting it might be a surviving relic from the early universe, when galaxy mergers were more common. Studying such extreme systems helps astronomers understand the full range of possible black hole-galaxy relationships and how they form. At the other end of the spectrum are dwarf galaxies with relatively small black holes. The galaxy NGC 4395, for instance, contains a black hole of only about 300,000 solar masses, among the smallest confirmed supermassive black holes. Despite its modest mass, this black hole shows AGN activity, with jets and variable emission detectable across wavelengths. Studying these low-mass systems reveals how black holes behave when they're just barely in the supermassive regime, bridging the gap between stellar mass black holes and the monsters like M87. Sagittarius A's intermediate mass, between the extremely small and extremely large, makes it perfect for comparative studies. It's large enough to show clear relativistic effects and to be resolvable with current technology, yet small enough that the timescales for orbital motion and variability are human-accessible. Stars complete orbits in years to decades rather than millions of years. Flares and variability occur on timescales of minutes to hours. This makes Sagittarius A an ideal laboratory for studying black hole physics in real time. The study of quasars, the most luminous class of AGN, provides additional context. Quasars are powered by supermassive black holes, accreting at extremely high rates, often approaching the Eddington limit where radiation pressure nearly balances gravity. They can outshine their host galaxies by factors of thousands, visible across billions of light years. The most distant quasars discovered date to when the universe was less than 1 billion years old, demonstrating that supermassive black holes formed early in cosmic history. These distant quasars pose a puzzle. How did black holes of billions of solar masses form so quickly, starting from stellar mass seeds of tens to hundreds of solar masses, reaching billions of solar masses through accretion, requires sustained feeding at very high rates for hundreds of millions of years. Observations suggest this happened, but the mechanisms remain uncertain. Did the seeds form from population 3 stars, the first generation of stars in the universe? Did some regions undergo direct collapse, forming massive black hole seeds without going through a stellar phase? Did hierarchical mergers of smaller black holes accelerate the growth? Sagittarius A can't directly answer these questions about the early universe, but it provides crucial constraints. By studying how a typical supermassive black hole behaves today, astronomers can build models of black hole growth that extend back to early times. By measuring Sagittarius A's current mass, spin, and properties, and comparing them with what we infer about its history from the Milky Way's assembly, we test whether our growth models make sense. If the models predict Sagittarius A should have very different properties than observed, something is wrong with our understanding of black hole evolution. The future merger between the Milky Way and Andromeda galaxies provides another point of comparison. Andromeda contains a central black hole of about 200 million solar masses, roughly 50 times more massive than Sagittarius A. When the galaxies merge, their black holes will eventually coalesce, creating a merged black hole of roughly 204 million solar masses after accounting for energy radiated as gravitational waves. This merger will be observable by LISA, the space-based gravitational wave detector, providing a direct measurement of how supermassive black holes merge in galaxy collisions. Studying merging supermassive black holes in other galaxies offers previews of what will happen to Sagittarius A. Astronomers have identified several systems containing pairs of supermassive black holes in close orbits, legacy systems from galaxy mergers where the black holes haven't yet coalesced. These binaries emit gravitational waves and can sometimes show periodic variations in their electromagnetic emission as the orbital motion modulates the accretion flow. The galaxy OJ 287, for example, shows periodic outbursts that may result from a smaller black hole periodically plunging through the accretion disk of a larger companion. Such systems represent snapshots of an ongoing merger process that will eventually end with coalescence. Understanding Sagittarius A also informs searches for intermediate mass black holes, objects between stellar mass and supermassive scales. These elusive objects might represent either the seeds from which supermassive black holes grow or the results of runaway stellar collisions in dense star clusters. Finding and characterizing intermediate mass black holes has proven challenging because they're too massive to form from ordinary stellar, collapse but too small to influence galactic structure, obviously. By understanding how Sagittarius A accretes and emits radiation, astronomers can better predict what signatures intermediate mass black holes should produce, guiding searches. The role of supermassive black holes in galaxy evolution extends beyond their immediate environment. When black holes launch jets or drive powerful winds, they inject energy into the intergalactic medium, the diffuse gas between galaxies. This energy can prevent gas from cooling and falling into galaxies, suppressing star formation on galactic and even cluster scales. Sagittarius A is too underluminous to have significant impact beyond the Milky Way itself, but by understanding the physics of how black holes couple to their surroundings, we can better model the effects of more powerful AGN on cosmic structure formation. Observations of Sagittarius A also constrain alternative theories of gravity. If Einstein's general relativity is not the final word, if modifications are needed on certain scales or in extreme environments, those modifications should affect black hole properties in measurable ways. By testing general relativity with Sagittarius A through stellar orbit observations, gravitational redshift measurements, and shadow imaging, astronomers place stringent limits on how much room there is for alternative theories. So far, general relativity passes every test. Any alternative theory must match general relativity's predictions at least as well as Sagittarius A observations allow, which is now extremely precise. The universality of black hole physics means discoveries at Sagittarius A immediately inform our understanding of black holes everywhere. When the Event Horizon Telescope detected hotspots orbiting near the event horizon of Sagittarius A, that finding implies similar processes occur near all supermassive black holes. When observations revealed strong organized magnetic fields around Sagittarius A, it suggested magnetic fields play similarly crucial roles around M87 and other black holes. Each detailed measurement at our galactic center extends our knowledge across the universe. This is the power of having a nearby laboratory. Sagittarius A will never be as spectacular as a bright quasar. It will never drive jets rivaling those from M87. It will never experience the feeding frenzy of a black hole in a colliding galaxy system. But its proximity and relative quiescence allow observations impossible anywhere else. We can resolve individual stars orbiting just outside the event horizon. We can watch flares evolve in real time. We can image the shadow at a resolution that reveals fine structure. These capabilities make Sagittarius A invaluable, despite its modest luminosity. As astronomy continues advancing, the symbiosis between observing Sagittarius A and understanding the broader black hole population will only deepen. Each new instrument, whether the next generation Event Horizon Telescope or future gravitational wave detectors, will provide data on both our galactic center and distant systems. By comparing them, astronomers will refine models of how black holes form, grow, and influence their cosmic environments. Sagittarius A serves as both a test case and a benchmark, the nearby monster that grounds our understanding of distant titans lurking in galaxies across the universe. One of the most revealing aspects of studying Sagittarius A comes from comparing it to M87, the other supermassive black hole imaged by the Event Horizon Telescope. These two objects could hardly be more different in some ways, yet strikingly similar in others. Understanding both their differences and similarities tells us profound things about how black holes work across a vast range of masses and environments. M87 sits at the center of Messier 87, a giant elliptical galaxy in the Virgo cluster, about 53 million light-years from Earth. It's a monster among monsters, containing 6.5 billion solar masses, over 1,500 times more massive than Sagittarius A. Despite this enormous mass difference and the vastly greater distance, M87 appears roughly the same size in the sky as Sagittarius A because of the mass-distance relationship. A more massive black hole has a proportionally larger event horizon, so even though M87 is 2,000 times farther away than Sagittarius A, it's also 2,000 times more massive, making its apparent size similar. But the similarities end there when you look at the environments. M87 sits in a giant elliptical galaxy, formed from multiple mergers of smaller galaxies. These mergers funneled enormous amounts of gas toward the center, feeding the black hole and allowing it to grow to its current tremendous mass. M87 is actively feeding. It consumes gas at a substantial rate, enough to power a brilliant active galactic nucleus. The black hole doesn't just glow with the energy of infalling matter, it launches a relativistic jet, a narrow beam of matter and energy that extends for thousands of light-years beyond the galaxy, moving at nearly the speed of light. This jet is one of the most spectacular features in all of astronomy. It's visible across the electromagnetic spectrum from radio waves to X-rays. The jet carries enormous power away from the black hole, more energy than the entire Milky Way emits from all its stars combined. The mechanism that launches the jet involves magnetic fields threading the accretion disk and tapping into the black hole's rotational energy. As gas spirals into the black hole, magnetic field lines get twisted into a helical configuration. These field lines act like a cosmic particle accelerator, flinging matter outward at relativistic speeds along the black hole's rotation axis. Sagittarius A shows no such jet, at least not a strong one. There's evidence for weak, intermittent outflows, but nothing remotely comparable to M87's spectacular beam. This difference reflects the feeding rate. M87 consumes matter voraciously. Sagittarius A barely nibbles. The accretion rate at Sagittarius A is perhaps 10,000 to 100,000 times lower than at M87. With less gas falling in, There's less energy available to power jets and outflows. The black hole is essentially starving, subsisting on whatever scraps of gas happen to lose enough angular momentum to spiral inward. Why the difference in feeding rates? It comes down to environment. M87 is a giant elliptical galaxy with a massive reservoir of hot gas in its core. This gas is readily available for the black hole to consume. The Milky Way, in contrast, is a spiral galaxy with most of its gas distributed in a thin disk far from the centre. The galactic centre region has relatively little gas compared to the galaxy's total mass. What gas exists there is hot and turbulent, difficult for the black hole to capture. So Sagittarius A starves while M87 feasts. Yet despite these dramatic differences in feeding rate, the Event Horizon Telescope images of the two black holes look remarkably similar. Both show bright rings surrounding dark shadows. Both have asymmetric brightness distributions around the ring. Both have shadow sizes that match general relativity's predictions. This similarity is profound. It suggests that the fundamental physics governing black holes is universal. Whether a black hole is 4 million solar masses or 6.5 billion, whether it's actively feeding or quiescent, whether it's in a spiral galaxy or an elliptical galaxy, the basic structure of the space-time around it follows the same rules: Einstein's equations. The bright ring in both images comes from the photon sphere, where light can orbit the black hole. The shadow comes from the region where all light inevitably falls into the event horizon. These features depend only on the black hole's mass and spin, not on the details of the accretion flow. So even though the environments are completely different, the fundamental geometry is the same. However, there are subtle differences worth noting. M87's ring appears more uniform in brightness in the average image, though it too shows variability. Sagittarius A's ring shows more pronounced asymmetry and variability, reflecting the more turbulent nature of its accretion flow. M87's gas orbits on timescales of days to weeks. Sagittarius A's gas orbits in minutes. This means Sagittarius A is constantly changing on human observational timescales, while M87 appears relatively static during a night's observation. The spin of the two black holes also differs. Measurements suggest M87 is spinning rapidly, perhaps at 60 to 90% of the maximum possible spin. Sagittarius A appears to be spinning more slowly, maybe 30 to 60% of maximum. This difference likely reflects their formation and growth histories. M87 probably grew primarily through smooth accretion of gas from a preferred direction, which spins the black hole up over time, Sagittarius, and might have grown through a combination of accretion and mergers with other black holes from random directions, which can spin the black hole down or leave it with moderate spin. Comparing the two black holes also reveals how accretion physics scales with mass. Theoretical models predict that smaller black holes should have more variable accretion flows because the orbital timescales are shorter and turbulence develops more rapidly. Sagittarius A confirms this prediction. Its flares and brightness variations happen on timescales of minutes to hours. M87 shows variability too, but on longer timescales of days to months. The basic physics is the same: turbulence and magnetic field instabilities in hot gas, but the timescales differ because of the mass difference. Another important comparison involves the immediate environment. M87 is surrounded by a vast reservoir of hot gas extending for thousands of light years. This gas is visible in X-rays glowing at tens of millions of degrees. The gas slowly cools and flows toward the centre, feeding the black hole and powering the jet. Sagittarius A has a much more modest surrounding environment. The hot gas around it extends for perhaps tens of light years, not thousands. The density is lower, the temperature is comparable, but the total mass of gas available is much smaller. These environmental differences have consequences for the black hole's future evolution. M87 will likely remain active for billions of years, continuing to consume the surrounding gas and launching jets that shape the galaxy around it. Sagittarius A will probably remain quiet unless something dramatic happens, like a gas-rich galaxy falling into the Milky Way or a major disturbance funneling gas toward the centre. The upcoming collision with Andromeda in 4 billion years will provide such a disturbance, temporarily transforming Sagittarius A into an active galactic nucleus comparable to M87's current state. Studying both black holes together allows astronomers to test theories that would be impossible to verify with only one object. For instance, theories about how magnetic fields amplify in accretion disks, how jets are launched, how variability patterns relate to accretion physics, all can be tested by comparing two systems with vastly different parameters. If a theory correctly predicts the behavior of both Sagittarius A and M87, it's probably capturing something fundamental. If it only works for one or the other, the theory needs refinement. The Event Horizon Telescope collaboration explicitly designed their observing campaign to image both black holes for exactly this reason. By having two reference points at opposite ends of the mass spectrum for galactic black holes, they can interpolate and extrapolate to understand black holes throughout the universe. Every supermassive black hole from a few 100,000 solar masses to tens of billions exists somewhere on the spectrum between Sagittarius A and the largest monsters known. Understanding the endpoints helps understand everything in between. Future observations will deepen these comparisons. The Event Horizon Telescope will continue monitoring both black holes, watching how they change over time. They'll observe at multiple wavelengths, revealing different aspects of the accretion flow and jet. They'll add more telescopes to the array, improving image quality and time resolution. Eventually, we might have movies of both black holes, showing gas swirling around them, matter falling in, variability playing out in real time. These observations will test general relativity in increasingly extreme regimes and reveal the detailed physics of accretion and jet formation. The comparison between Sagittarius A and M87 embodies one of science's most powerful approaches, studying extremes to understand the middle. By examining the quietest and one of the most active supermassive black holes we can observe in detail, astronomers bracket the range of behaviors and test whether our theories are truly universal. So far, general relativity has passed every test. The shadows match predictions. The ring sizes match predictions. The basic geometry follows Einstein's equations. This is remarkable considering those equations were written over a century ago, long before anyone imagined we could observe black holes directly. Yet they work, from the smallest scales we can test to the largest structures in the universe, from weak gravitational fields to the extreme curvature near event horizons. The monsters are different, but the mathematics describing them is the same. The study of Sagittarius A is far from complete. Despite decades of observations and the recent triumph of the Event Horizon Telescope, many fundamental questions remain unanswered. How did the black hole form? What is its exact spin? How does the accretion flow behave on the smallest scales? What triggers flares? Can we detect deviations from general relativity? Will the black hole become more active in the near future? Each question opens pathways for new observations and theoretical work. The Event Horizon Telescope continues to improve. New telescopes are being added to the network, increasing sensitivity and allowing observations at multiple wavelengths simultaneously. The Greenland Telescope joined in 2018, adding coverage in the Northern Hemisphere and improving the north-south resolution of the array. The Kitt Peak Telescope in Arizona was added more recently. Future additions might include telescopes in Africa, additional sites in South America, and potentially even a space-based telescope to extend the baseline beyond Earth's diameter. Each addition makes the array more powerful and capable of probing finer details around the black hole. Observations at shorter wavelengths are also planned. The current Event Horizon Telescope operates at 1.3 mm wavelength. Observing at shorter wavelengths, perhaps 0.87 mm, or even shorter, would provide sharper images and reveal smaller scale structure. The challenge is that atmospheric water vapor absorbs these wavelengths strongly, requiring extremely dry conditions. The Atacama Desert in Chile and high-altitude Antarctic stations are ideal for such observations. If successful, shorter wavelength observations could resolve the structure of the event horizon shadow in much finer detail and potentially even detect the photon ring, a thin, bright ring predicted to exist just outside the shadow. Multi-wavelength observations combining radio, infrared, X-ray and gamma-ray data promise to reveal how different parts of the accretion flow and jets behave. Coordinated campaigns with space-based and ground-based telescopes allow astronomers to trace energy flow from the outer accretion disk down to the event horizon. For instance, the gravity instrument on the Very Large Telescope in Chile can observe Sagittarius A simultaneously with the Event Horizon Telescope, providing infrared measurements of hotspots in the accretion flow, while the radio observations probe the larger scale structure. Combining these data sets creates a more complete picture of the environment than any single instrument could provide. The James Webb Space Telescope has also begun monitoring Sagittarius A. Its infrared cameras can observe flares and variability with exquisite sensitivity, complementing the Event Horizon Telescope's radio observations. Webb's observations have already revealed flickering and flaring on short timescales, suggesting that the innermost accretion flow is highly dynamic and variable. Future observations will track how flares evolve and potentially identify their physical origin. Looking further ahead, space-based gravitational wave detectors will revolutionize the study of supermassive black holes. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect gravitational waves from merging supermassive black holes across the universe. When black holes merge, they emit gravitational waves with frequencies that depend on their masses. LISA is designed to detect waves from supermassive black hole mergers, including systems similar to or larger than Sagittarius A. By detecting the gravitational wave signal, astronomers can measure the masses and spins of merging black holes with extraordinary precision, far better than electromagnetic observations allow. LISA will also detect continuous gravitational waves from close binary systems orbiting supermassive black holes, systems too faint to be seen in electromagnetic radiation, but bright in gravitational waves. If Sagittarius A has any massive objects, perhaps stellar mass black holes or neutron stars, in tight orbits around it, LISA might detect them. This would provide a completely new way to probe the black hole's environment and test general relativity. Closer to the present, astronomers continue tracking the S-stars with ever greater precision. The next pericenter passage of S2 will occur in the early 2030s. By that time, instruments will have improved, allowing even more sensitive tests of relativity. Astronomers hope to measure frame dragging, to detect orbital precession to higher sigma significance, and to search for any anomalies that might hint at new physics. The discovery of stars with even shorter orbital periods, if they exist, would provide even better tests. There are ongoing surveys searching for such stars. The accretion flow remains incompletely understood. Despite all the observations, the exact mechanisms that transport angular momentum outward, allowing gas to spiral inward, are not fully clear. Magnetic fields certainly play a role, but the detailed physics of magnetohydrodynamic turbulence in the accretion flow is complex and requires sophisticated computer simulations to model. Comparing these simulations to observations helps refine our understanding. Future campaigns will test specific predictions from simulations, looking for signatures of magnetic field structures, turbulent eddies, and shock waves in the flow. One of the great hopes is to make movies of Sagittarius A. A single image, while revolutionary, captures only one moment in time. A movie showing how the gas flows around the black hole over minutes to hours would reveal the dynamics directly. This requires observing the black hole continuously for extended periods with high time resolution. It's technically challenging because the array must track the source as Earth rotates, and data processing must handle the rapid variability. But if successful, movies would transform our understanding of accretion processes and might reveal unexpected phenomena. The long-term fate of Sagittarius A is also of interest, particularly in the context of the upcoming merger with Andromeda. Simulations of galaxy mergers show that the central black holes of the merging galaxies eventually coalesce, but the exact timeline and dynamics depend on the galaxy's initial conditions. Observing pre-merger binary supermassive black hole systems in other galaxies provides insights into what will happen when Sagittarius A and Andromeda's black hole merge. These observations inform models of how black holes influence galaxy evolution, and how mergers affect star formation and gas dynamics. Finally, the philosophical and scientific implications of studying Sagittarius A extend beyond astrophysics. Black holes challenge our understanding of reality at the most fundamental level. They force us to confront the limits of knowledge. What happens inside an event horizon cannot be observed from outside. The information that falls in appears to be lost, violating principles of quantum mechanics that say information must be conserved. This information paradox, first raised by Stephen Hawking, remains unresolved despite decades of theoretical work. Sagittarius A is our closest laboratory for confronting these deep questions. Every observation of matter and light near the event horizon provides data that must be reconciled with theory. If general relativity is not the final word on gravity, if quantum mechanics requires modification at large scales, If information truly is lost in black holes, observations of Sagittarius A will eventually reveal the evidence. The black hole is a cosmic Rosetta Stone, a place where the rules are written in the language of extreme physics. We stand on the threshold of a new era in black hole astronomy. For the first time in history, we have the technology to observe supermassive black holes directly, to watch matter spiral into oblivion, to test the most extreme predictions of relativity. Sagittarius A leads the way because of its proximity and observability. Every discovery made at the Milky Way's center illuminates the nature of black holes throughout the universe. And every observation reminds us that we live in a galaxy anchored by a monster, a 4 million solar mass titan lurking in the darkness, patient and eternal. The journey of discovery continues. The monster awaits. As we conclude this exploration of Sagittarius A, it's worth reflecting on what this cosmic monster represents for humanity's understanding. For most of human history, black holes were mathematical curiosities that most assumed would never correspond to real objects. Yet, here we are, having photographed one at the heart of our own galaxy. This achievement represents a triumph of human ingenuity and international collaboration. The Event Horizon Telescope required coordination across continents, synchronizing atomic clocks to billionths of a second, processing petabytes of data, and developing new algorithms. In an era often marked by division, the collaboration stands as a testament to what humanity can accomplish together. The existence of Sagittarius A puts our place in perspective. We orbit this black hole at 26,000 light-years, completing one circuit every 225 million years. Everything we've known has occurred during a tiny fraction of one galactic orbit. Our entire species is younger than 1% of a galactic year. The black hole was ancient when first cells formed on Earth. It will still be there long after our sun dies. Yet despite the black hole's overwhelming scale, we're not helpless before it. We've measured its mass to extraordinary precision, watched stars dance around it, photographed its shadow, and tested Einstein's predictions. We've transformed a region of complete mystery into a laboratory for fundamental physics. The discoveries continue. We're learning that supermassive black holes are dynamic systems that evolve over cosmic time, shaped by formation history, mergers, and cycles of feeding. We're discovering the environment around Sagittarius A is far more complex than models suggested, with magnetic fields, turbulent flows, and exotic objects all playing roles. Perhaps most importantly, Sagittarius A reminds us the universe still holds profound mysteries. We don't fully understand how supermassive black holes form, how accretion flows work in detail, what happens inside event horizons, or how quantum mechanics and gravity reconcile. These questions represent the frontiers where theory meets observation. The future is bright. New telescopes and techniques promise to reveal details we can barely imagine. Perhaps we'll make movies showing gas flowing around the event horizon in real time. Perhaps we'll detect gravitational waves from objects spiraling in. Perhaps we'll find evidence for quantum gravity. Or perhaps Sagittarius A will surprise us in ways we haven't anticipated. Whatever discoveries await, the monster at our galaxy's center will continue to captivate and challenge us. It's been there for billions of years and will be there for billions more. We're privileged to live when technology and knowledge have advanced enough to turn the invisible into the visible, the theoretical into the observable. So when you look towards Sagittarius, remember that beyond all visible stars, beyond the dust and gas, there sits a monster 4 million times more massive than the Sun. You're orbiting it right now at 500,000 miles per hour, held in the gravitational embrace of an object that represents gravity's ultimate expression. It's Sagittarius A, the heart of the Milky Way, the monster we've learned to photograph, measure, and begin to understand. We've barely begun to unravel its mysteries. If you've enjoyed exploring the cosmic monster at the heart of our galaxy, consider giving this video a like and subscribing to Space Reports for more journeys into the mysteries of the universe. The cosmos has many more secrets waiting to be revealed,